Imagine that you're standing on the edge of a boundless ocean, with a sparkling cosmos reflected in its waters. Now imagine that this panorama, with its myriad stars and spinning galaxies, is just a reflection, a projection from an invisible, distant shore. This is not the beginning of a science fiction tale, but a look at one of the most striking theories in modern physics: the holographic principle. Just as each droplet on a spider's web contains the world in miniature, our universe may be a grand reflection of fundamental laws written on a distant frontier. Far from the solid earth beneath our feet and the emptiness of space, the very fabric of our reality may be generated by something much deeper, something beyond our present comprehension. Let's go on this exploration together and try to answer the ultimate question: does the fabric of our universe arise from a holographic boundary? At the heart of physics is a quest to uncover the layers of reality to reveal its most fundamental elements. These elements, known as ontological primitives, are the foundation upon which the vast edifice of the universe is built. For centuries, physicists have searched for these building blocks, seeking to understand the rules governing their interactions. The journey begins with the concept of space. Isaac Newton, one of the titans of science, envisioned space as an absolute, unchanging background, indifferent to the comings and goings of matter and energy. For Newton, space was an absolute receptacle, an infinite space in which all the events of the universe were played out. However, as our understanding deepened, this view of space began to evolve. The advent of Einstein's theory of relativity painted a different picture, in which space was not just a passive arena, but an active participant in cosmic interaction. According to the new view, space could bend and curve in the presence of mass and energy, calling into question the very notion of its absoluteness. Amid the shifting perspectives, a radical idea emerges: the holographic principle. This principle suggests that our three-dimensional perception of the universe may be akin to a hologram, a projection from a two-dimensional surface located at the edge of space. This edge, though infinitely distant and inaccessible to direct observation, may contain the fundamental information that gives rise to everything we perceive as reality. This concept overturns our usual notions by arguing that the very essence of space, the fabric of our reality, may not be a fundamental characteristic of the universe, but is emergent. Emergentism describes phenomena that arise from the complex interaction of simpler elements, leading to new properties and behaviors that are not obviously based on the components alone. In the context of our universe, and especially within the holographic principle, emergentism takes on a fascinating role. Here, the term implies that the three-dimensional space we move through and the time we experience are not the fundamental building blocks of reality. Instead, they arise from a more basic two-dimensional structure, the holographic boundary that encodes the information and laws that give rise to our perceived reality. In this framework, every star, planet, and galaxy, every law of physics, from gravity to electromagnetism, and the very fabric of the cosmos, are emergent phenomena. It's something like a bridge between the known and the unknown, between the observable dimensions of our universe and the fundamental coding of reality at the holographic boundary. It invites us to rethink not only the structure of the cosmos, of reality, as we peel back the layers of the universe. Against the backdrop of our hypothesis, black holes, where gravity triumphs to such an extent that even light can't escape it, have become those unexpected heroes, thanks to the pioneering insights of Stephen Hawking and Jacob Bekenstein. Hawking and Bekenstein ventured into uncharted territory by attempting to combine the fields of quantum mechanics and general relativity theory in order to explore the thermodynamics of black holes. Their theories reveal the startling fact that black holes are not absolute endpoints of entropy, but rather key players in the cosmic interaction of information and energy. Entropy, traditionally associated with disorder in a system, took on a new dimension in their hands. It became a veil hiding information inside black holes. It wasn't just about the randomness or disorder of particles, but about the hidden layers of information that define the very structure of reality. As matter spirals into a black hole, it seems to disappear from our universe, which raises a major question. What happens to the information it carries? This question calls attention to entropy, not just as a measure of disorder, but as a key to understanding the fate of ingested information. The entropy of a black hole, as proposed by Bekenstein, is directly proportional to its surface area, not its volume, a concept that contradicts our everyday understanding of physical laws. This relationship between surface area and entropy leads us to a profound conclusion. The maximum amount of information that can be contained in any given region of space is determined not by its volume, as one might intuitively assume, but by its surface area. This view laid the foundation for the holographic principle, which assumes that all the information of a volume can, in principle, be encoded on a two-dimensional surface. Thus, Hawking and Bekenstein's discoveries of black hole thermodynamics suggest a cosmos in which the very fabric of reality, every particle, every force, and the very dimensions of space and time can only be emergent properties, emerging from a deeper two-dimensional fabric. At the forefront of bridging the gap between the mysteries of black hole thermodynamics and the holographic principle is Juan Maldacena's ADS-CFT correspondence. This work is not just a framework, but a concrete example of holographic principles in action. Maldacena's correspondence asserts a duality between a type of space known as anti-de Sitter space, abbreviated ADS, and conformal field theory, or CFT, which exists at the boundary of this space. Despite the positive cosmological constant of our universe, which contrasts with the negative constant of ADS space, derived from this duality provide insight into the nature of gravity and quantum mechanics, and, by extension, the holographic nature of our universe. Central to this dualism is conformal field theory, which operates on the boundaries of the universe within the ADS-CFT framework. CFT is unique in its scale invariance. The laws governing these field theories remain unchanged, regardless of the size or scale at which they're observed. This property of CFT is key because it encodes the information needed to describe higher dimensional bulk space within a lower dimensional framework, effectively illustrating the holographic principle. Scale invariance within CFT is not just a mathematical curio, it's a window into the emergence of dimensions and the very fabric of space itself. Different scales of patterns at the boundary, governed by the uniform laws of CFT, contribute to the illusion of three-dimensional space. This phenomena emphasizes the holographic principle that the complexity and dimensions of volume space arise from simpler scale-variant dynamics at the boundary. Through the prism of ADS-CFT and the intricacies of conformal field theory, we gain a deeper understanding of how the dimensions and the very structure of space-time can emerge. Scale-invariant boundary patterns, each contributing to the holographic encoding of the universe. One of the most obvious metaphors for this complex idea is the concept of nested spheres. These nested spheres serve as a visual framework, with each layer representing different scales of boundary patterns. The finest patterns, akin to the microscopic level, are densely packed with information and require high-resolution understanding. As you move to finer spheres, the patterns become coarser, encapsulating the same information, but in a more generalized, less detailed form. In the microscopic space of the holographic boundary, the patterns are dense and highly detailed, resembling the fine strokes of a master painter. These fine-grained patterns are the most fundamental level of the universe, where every tiny element is filled with information encoding the laws of physics and initial conditions of cosmic phenomena. Moving from the micro to the macro environment resembles looking at a mosaic. Up close, we see only individual tiles, each with its own color and shape, but at a distance, a complex and holistic image emerges. Similarly, the grand structure of the universe, galaxies, stars, and planets, emerges from the collective behavior of fundamental patterns encoded on the holographic boundary. This transition from fine to coarse-grained patterns at the boundary of the universe is not just a feature of the holographic model. It's a fundamental process that shapes our perception of space. It emphasizes the difference in information requirements at different scales, demonstrating the adaptability and efficiency of the holographic encoding of space. This concept of a holographic universe is based on a profound philosophical and scientific notion, ontological democracy. This idea suggests that the boundaries of the universe, with its two-dimensional encoding of information and the three-dimensional space we're all familiar with, can be equally fundamental to the fabric of reality. Neither is more real or primary than the other. Rather, they coexist in a state of mutual emergence. This view has far-reaching implications. It suggests that what we perceive as the three-dimensional reality of stars, galaxies, and planets, with all their complex interactions, may be a manifestation of deeper, more fundamental laws encoded at a distant, invisible boundary. This coding not only dictates the structure of the volume, but is also shaped by events within it, creating a feedback loop. In our journey through the holographic universe, we encounter a profound rethinking of gravity, which is traditionally viewed as the curvature of space-time under the action of mass. In the holographic framework, gravity arises not from mass itself, but from entropic forces acting on the information encoded at the boundary of the universe. The idea that gravity might be an emergent phenomenon, like temperature or pressure in thermodynamics, represents a radical shift in perspective. It suggests that what we perceive as gravitational attraction is the result of the universe's tendency to maximize entropy, an idea first proposed by physicist Eric Verlinde. This theory suggests that gravitational attraction arises from changes in the amount of information associated with the position of material bodies. The holographic universe also pushes us to explore the mysterious role of quantum entanglement in the fabric of space-time. Quantum entanglement, the phenomena in which particles remain bound in such a way that the state of one particle can instantaneously affect the state of another, regardless of the distance separating them, may be the thread that weaves the spatial continuum of the universe. According to this view, space itself arises from the entanglement of quantum bits encoded at the cosmic boundary. When particles are entangled, they share a common bond that contributes to the illusion of continuous space. Theoretically, unraveling these particles could lead to the disappearance of the space between them, which calls into question the very notion of distance and locality in our universe. The principle of a holographic universe, of course, like many other theories in physics, poses one ultimate question: the question of finding a universal holographic model. This ambitious endeavor is designed to reconcile the myriad complexities of the universe into a single structure that accurately describes both the immense cosmic scale and the minutiae of quantum mechanics. The challenges in this endeavor are enormous. Creating a universal model requires not only a deep understanding of quantum mechanics and the general theory of relativity, but also a new approach to integrating these theories into a holographic framework. Potential breakthroughs promise to revolutionize our understanding of the cosmos. A successful, universal holographic model could provide unprecedented insights into the origin of the universe, the nature of black holes, and the fundamental laws governing reality. As we journey through the possibilities of the limits of this theory, we may be on the threshold of a new understanding of the cosmos, or another refutation of a high-profile theory. If reality is holographic, then our perception, experience, and very existence may be far more intertwined with the cosmos than we ever imagined. This journey is fraught with challenges and unknowns, but the promise of unlocking the deepest secrets of the universe propels us forward in pursuit of an elusive universal model that will redefine our place in the cosmos. In the vast theater of our solar system, where planets like Jupiter and Saturn often attract attention with their majestic rings and violent storms, lies a distant world shrouded in mystery and intrigue. This is Uranus, an enigmatic ice giant that often goes unnoticed, but holds secrets that may unravel some of the most enduring mysteries of the cosmos. Far beyond the asteroid belt, nestled between the orbits of Saturn and Neptune, Uranus travels through the cold and dark corners of our solar system. It's a world that lives at a different rhythm, spinning on its side, an oddity that's long puzzled astronomers and spawned countless theories. Discovered in 1781 by William Herschel, Uranus was the first planet discovered through a telescope, extending the known boundaries of our solar system. For centuries, this distant world was just a speck of light in our telescopes, a ghostly blue ball, distant and aloof, keeping its secrets. But now, with the advent of the James Webb Space Telescope, a new chapter in the exploration of Uranus is opening. JWST, with its unprecedented vision, peels back the layers of this icy giant, revealing a world of amazing beauty and complexity. Let's travel together to this mysterious ice giant and learn about the latest discoveries made by the James Webb Space Telescope. In the quest to understand the universe, humankind has launched a sentinel into space, a marvel of engineering and a testament to our insatiable curiosity. This sentinel is the James Webb Space Telescope, the most advanced and powerful space telescope ever built, the successor to the legendary Hubble Space Telescope. Equipped with a set of advanced instruments and a mirror more than 6.5 meters in diameter, JWST is designed to observe the universe in light invisible to the human eye, the infrared spectrum. This allows the telescope to peer through clouds of cosmic dust, discover distant galaxies, and study the atmospheres of exoplanets. The telescope's journey into space was a feat in itself. Launched on an Ariane 5 rocket, JWST traveled to a point in space known as the Second Lagrange Point, or L2, 1 million miles from Earth. Here, in this stable orbit, JWST can observe the universe with minimal interference from Earth and the Sun. JWST's capabilities are not limited to observing the early universe or distant galaxies. It plays a key role in unlocking the mysteries of our solar system. Its powerful instruments, such as the near-infrared camera, NIRCam, and the mid-infrared instrument, MIRI, reveal new details about planets, moons, and other celestial bodies closer to home. Take Uranus, for example. In the past, our view of this distant planet was limited to faint images from telescopes such as Hubble. But now, thanks to JWST's enhanced infrared capabilities, we can see Uranus in a new light. The telescope's sensitive instruments allow us to observe the planet's atmosphere, weather patterns, and even its mysterious rings with unprecedented clarity. By analyzing the light of Uranus, JWST can decipher the chemical composition of its atmosphere, revealing the presence of gases such as methane and hydrogen. This not only helps us understand the current state of Uranus, but also provides clues about its formation and evolution. The James Webb Space Telescope continues to exceed expectations, revealing more details about our universe every day. Its latest triumph is a series of images of Uranus taken very recently, surpassing even the stunning observations made in April 2023. In early 2023, JWST provided us with unprecedented views of Uranus, allowing us to look at the planet's atmospheric dynamics and ring system in a new light. The recent images, however, are a step further. Not only are they clear, they reveal aspects of Uranus that were previously hidden or obscured, even in April observations. Take the rings of Uranus, for example. The latest images show them with even greater clarity. We can now observe finer structures within the rings and even detect faint dust bands that were previously invisible, such as the Zeta ring, the incredibly thin ring closest to the planet. The strength of JWST lies not only in its one-off observations, but also in its ability to continuously track celestial objects. Continuous observations of Uranus have allowed us to observe changes in the planet's atmosphere, track the movement of its clouds, and observe the evolution of its storms over time. The changes in the polar regions are particularly striking. Bright white caps and dark bands near the poles, the origin of which is still unclear, have shown marked changes. This continuous observation provides invaluable data for understanding the seasonal changes and long-term climate patterns of Uranus. In the set of planets in our solar system, Uranus stands out with a peculiar feature, an extraordinary axial tilt. Unlike any other planet, Uranus rotates practically on its side, tilted at an angle of about 98 degrees. This unique orientation has long intrigued astronomers and sparked a quest to understand its origin and consequences. To understand the significance of this tilt, we must travel back in time to the early days of our solar system. Uranus probably formed with a much less severe tilt. The prevailing theory suggests that a catastrophic event, perhaps a collision with a planet-sized object, dramatically changed its orientation. This colossal impact would have thrown Uranus aside, changing the definition of its axis of rotation. Such a dramatic event in the planet's history probably not only changed its rotation, but also left an indelible mark on its entire system, including its satellites and rings. Today, this lateral rotation is a unique spectacle. Each pole of Uranus is alternately flooded with sunlight and plunged into darkness at intervals of 42 years. This extreme tilt results in extreme seasons, unlike those observed on other planets. The implications for planetary observations and research are enormous. Uranus's tilt allows us to observe its rings and satellites from different perspectives, offering insights into their composition and dynamics. For example, when Uranus's rings face the Earth, they become nearly invisible, exposing fainter dust bands and smaller satellites. Compare that to Earth, which is tilted only 23.5 degrees. Uranus's extreme tilt causes drastic changes in its weather patterns, which is a goldmine for scientists studying planetary climate. Tilt also affects the circulation of Uranus's atmosphere. Prolonged exposure to sunlight at the poles can result in complex weather systems, as seen in recent JWST images. These systems are very different from those on other planets and provide a unique laboratory for understanding atmospheric physics. Let's take a journey on one Uranian year. Each season on Uranus lasts about 21 Earth years, a consequence of its 84-year orbit around the Sun. This extended duration means that each hemisphere experiences long periods of daylight, followed by equally long nights. As a result, the planet undergoes dramatic changes in appearance and climate. Because one pole of Uranus basks in uninterrupted sunlight, summers are long, while the opposite pole plunges into a deep, dark winter. This stark contrast creates unique atmospheric conditions, causing complex weather patterns and climatic shifts. The impact of these seasonal changes on Uranus's atmosphere is profound. When the sun illuminates the planet's surface, it warms the atmosphere, creating colossal storms and dynamic cloud systems. These atmospheric phenomena are not static. They evolve and change with the seasons, painting an ever-changing portrait of the planet. Among the most striking features are the bright cloud tops that appear when the sun illuminates the planet's atmosphere. These clouds, composed of frozen methane and other gases, reflect sunlight, creating a dazzling spectacle. Conversely, dark storm patches that look like giant hurricanes roam the planet's surface. Moreover, the planet's seasonal phenomena affect not only the planet itself, but also its moons. One recent study of Uranus's moons, or rather a phenomenon that's particularly intriguing, is the development of temporary atmospheres on these moons, a spectacle caused by the unique conditions of the Uranus system. The key to understanding these temporary atmospheres lies in the extreme tilt of Uranus's axis and its effect on the satellite's orbits. As these satellites orbit the planet, they experience dramatic changes in solar exposure, alternating between long periods of intense sunlight and prolonged darkness. During the long summer exposed to sunlight, the icy surfaces of these satellites undergo a process known as sublimation. The ice, composed mainly of water, methane, and carbon dioxide, transforms directly from solid to a gas, bypassing the liquid phase. This sublimation creates thin, temporary atmospheres, or exospheres, that envelop the satellites. These exospheres are most pronounced when moons are warmest. Recent research by the James Webb Space Telescope shows that this phenomena is more dynamic and complex than previously thought. Exospheres are heterogeneous. They vary in composition and density, depending on the topography of the moons and the intensity of solar radiation. As the satellites enter their winter phase, the exospheres gradually dissipate. Gases recondense on the surface, returning to an icy state. This cycle of atmosphere creation and disappearance is a unique characteristic of Uranus's satellites, opening a window into the interaction between solar radiation and surface ice. The rings of Uranus, often overshadowed by the majestic rings of Saturn, hold their own tale of cosmic intrigue and dynamism. A recent comparative study of the rings of Uranus, Saturn, and Jupiter sheds new light on these lesser-known, but no less fascinating, celestial features. In contrast to the wide and bright rings of Saturn, the rings of Uranus are narrow, dim, and less extensive, extending to 4 planetary radii. This includes elusive rings, such as the Mu and Nu rings. The study delves into the gravitational influence of Uranus's main satellites on these rings, a key factor in their formation and evolution. The significant influence of Uranus's 5 major satellites, Miranda, Ariel, Umbriel, Titania, and Oberon, plays a central role in the history of the rings. These satellites, much more massive than their smaller counterparts, dominate the gravitational dynamics within the Uranus system. Their positions and masses relative to Uranus provide a better understanding of the formation of the satellites and the gravitational formation of the rings. The formation of Uranus's rings is attributed to a combination of processes, including collisions, satellite breakup, and gas release from the main satellites. These dynamical processes affect the material composition of the rings and are influenced by the ever-changing environment of the Uranus system. The stability of the rings is intrinsically linked to their dynamical interactions with the satellites of Uranus. The study examines how accretionary processes occur within the Roche limit and how the dynamics of shepherding moons play a crucial role in maintaining the rings. In addition, the rings provide a unique opportunity to understand the internal structure of Uranus through seismological studies. Modeling results show how these satellites shape the ring system, affecting its structure and stability over time. The modeling predicts significant material loss within the ring system, primarily due to gravitational interaction with the satellites. The complex dance between moons and rings is a key aspect of the Uranus system. The dynamic exclusion zones created by the satellites and the influence of these zones on the material distribution of the rings are crucial to understanding the structure and the evolution of the rings. The study also examines the role of satellite-to-satellite interactions in the evolution of the system, especially past resonances between satellites such as Ariel and Umbriel, and their impact on the orbits and geology of satellites, especially Miranda. But the mysteries surrounding this planet don't end there. You've probably heard of the Aurora Borealis. Well, the latest discovery concerns the auroras of Uranus, which also has them. However, its auroras, unlike Earth's, occur in the infrared spectrum. Using the Keck 2 telescope, astronomers observed enhanced emissions of trihydrogen cation in the planet's atmosphere. This is a groundbreaking discovery that sheds light on the unique magnetic field and dynamics of Uranus's atmosphere. Uranus's magnetic field, which is significantly deflected from the planet's axis of rotation, creates a unique coupling of the magnetosphere, ionosphere, and thermosphere. The detection of these infrared auroras is crucial because it opens up a new window into these processes, previously elusive due to the lack of such detections on Uranus. Comparing the polar auroras of Uranus with those of Jupiter and Saturn reveals their different characteristics. Unlike Jupiter, where the H3+ emissions have short lifetimes that smooth out the variability of the UV emission, the brightest infrared emissions of Uranus do not necessarily coincide with the brightest UV emissions of the other planets. This unique aspect of Uranus's polar lights provides valuable information for exoplanet studies, especially for the worlds of warm ice giants. The study delves deeper into the unusual heat spots on Uranus observed near the latitudes of the UV northern lights. These spots, analyzed for temperature, column density, and total emission, suggest that the enhancement is not caused by temperature, but rather by increased ionization, probably due to polar aurora activity. Polar lights play a significant role in heating the atmosphere, and on Uranus, the increased H3+ emissions associated with these auroras suggest their involvement in atmospheric processes. By studying such unique things, we gain a deeper understanding of similar processes in different planetary environments, enriching our knowledge of how auroras shape planetary atmospheres, affecting not only thermal properties, but also the overall dynamics of the ionosphere and magnetosphere. In the quest to unravel the mysteries of our solar system, the ice giants Uranus and Neptune are distant enigmas beckoning closer exploration. Recent research, including a fresh analysis of Voyager images, has revealed that the two planets actually have similar shades of greenish-blue color, fundamentally changing our long-held beliefs. Uranus and Neptune share many common characteristics, They're roughly the same size, have the same mass, and are surrounded by deep atmospheres of comparable materials. Nevertheless, it was long thought that their appearance was quite different. This misconception has now been corrected. Both planets are shown in their true colors, largely influenced by the methane layer in their atmospheres. The need for a dedicated mission to Uranus has never been greater. Such a mission would not only deepen our understanding of the planet itself, but also provide a comparative view of Neptune and other similar icy giants. The mission's potential goals range from studying the unique magnetic field and complex ring system to investigating atmospheric dynamics and internal structure. In an important achievement for planetary exploration, the Uranus Orbiter and Probe mission has been elevated to the highest priority for NASA flagship mission within the 2023-2032 Planetary Science Decadal Survey. Future launch windows are available between 2030 and 2034. Key science goals will include a detailed analysis of the unusual tilt of Uranus's axis and its effect on the planet's climate and weather patterns. The mission can also study the intriguing phenomena of infrared auroras and their role in heating the atmosphere, providing a comparative study with other planets. Studying Uranus and Neptune will also provide valuable information about planetary evolution and dynamics. Understanding why Uranus appears slightly whiter, perhaps due to its more stagnant atmosphere, allowing methane haze to accumulate, can tell us a lot about atmospheric processes on the ice giants. As we await a future mission to Uranus, we stand on the threshold of discoveries that could redefine our understanding of the outer solar system. Exploring this distant ice giant will not only unravel its mysteries, but will also expand our knowledge of planetology as a whole, shedding light on the complex picture of our cosmic home. Reality. We think we know what it is. The ground beneath our feet, the air we breathe, the world we see. But the deeper we look, the stranger it becomes. Did you know that what we perceive as solid matter is mostly space? The atoms that make up everything around us are 99.9% space. In addition, there is time. It's not a constant, ticking away in the background. Time can stretch, slow down, and even stop under the right conditions. So how much of what we experience is real, and how much is just a construct of our minds? What if the reality we trust is just a shadow of something deeper, stranger, and infinitely more complex? What is reality? For the first humans, the answer was simple. Reality was what they could see, hear, touch, and smell. The world around them was interpreted through their senses, guiding them through every day. The rustling of leaves signaled the approach of a predator. The distant crack of a branch indicated prey. And the sensation of warmth from a campfire chased away the cold night. This sensory reality was everything. Survival depended on it. Sight, hearing, touch, smell, these senses were the tools with which they cognized their environment. But for them, reality was limited to that which was accessible to direct perception. The invisible world beyond their senses was incomprehensible. Everything tangible became real. If a sound was heard, the danger was near. If an odor was smelled, food could be found. If something could not be smelled, it might not exist at all. Survival was a continuous process of interpreting these sensory cues, often in life or death situations. Recognizing the difference between the roar of a predator and the rustle of the wind could mean the difference between safety and death. Early humans lived in a world where reality was directly related to their immediate needs: food, shelter, protection. For them, reality was not questioned, it was lived through experience. However, as society evolved, the concept of reality also changed. The question of existence and meaning began to extend beyond the immediate environment. what lies beyond the senses, what forces shape the world. Over time, the limitations of direct perception have given way to imagination and conjecture. This curiosity led to the birth of new ideas, a reality that was no longer tied to the physical world. Early humans began to develop explanations for what they could not see or understand. Spirits, gods, and forces of nature became personifications of the unknown. Fire, lightning, and stars were attributed to forces beyond human control. Through mythology and beliefs, they created a wider reality that filled the gaps left by their sensory limitations. This cultural development marked a turning point in human thinking. Humanity's journey, which began with a simple need to survive, has now evolved into something much more complex. In one of the earliest philosophical explorations of reality, Plato presents this allegory of the cave. In this mental experiment, prisoners have been confined in a cave all their lives, seeing nothing but shadows projected on the wall in front of them. These shadows are all they know about. They mistake these flickering figures for reality itself. For them, the shadows are the only truth that they can perceive. But what if they broke free of their chains and turned around? What would they see? Plato's allegory suggests that human perception is often limited. What we perceive as reality may only be a shadow of a deeper, truer existence. The path to understanding true reality, Plato argued, begins with questioning the world as we perceive it. Plato's allegory is not just a philosophical exercise. It is a profound commentary on the limits of human perception. We may think we see the whole picture, but we're often limited by the limits of our senses and our experience. Reality can thus extend far beyond what we can directly observe. In the physical world, our understanding of reality underwent a significant change with the discovery of SpaceTime. In the early 20th century, Albert Einstein shattered the age-old foundation of classical physics by showing that space and time are not separate entities, as previously thought, but are instead interwoven into a single four-dimensional fabric, space-time. According to Einstein's general theory of relativity, massive objects warp this fabric, creating what we experience as gravity. Planets revolve around the sun, not because they're pulled by some invisible force, but because the sun warps space-time around itself, creating a curved path for them. This revolutionary concept has completely changed our view of reality on a cosmic scale. Time, too, is no longer absolute. In Einstein's universe, time can be stretched or compressed, depending on the speed at which an object is moving, or its proximity to a more massive object. This idea, time dilation, means that time itself is relative, which changes our perception of how reality unfolds. The scientific method has for centuries allowed us to peel back the layers of this reality. Classical mechanics, developed by Newton, gave us the tools to understand the motion of objects by accurately predicting their trajectories. But as we began to delve deeper into the nature of the universe, discoveries, especially in quantum mechanics and relativity theory, showed us that reality operates in ways that had previously defied common sense. The search for the basic building blocks of reality began thousands of years ago. Back in the 5th century BC, the Greek philosopher Democritus suggested that everything in the universe consists of tiny, indivisible particles, atoms. These atoms, he argued, are the fundamental building blocks of all matter. This idea persisted for centuries until modern atomic theory took shape in the 19th century. Scientists such as John Dalton began to provide empirical evidence that all matter was indeed made up of atoms. These tiny particles, invisible to the naked eye, joined together in various ways to form everything from the air we breathe to the stars in the sky. Atoms were long thought to be the most fundamental, indivisible units of the physical world. But as our understanding deepened, we discovered that the atom itself could be broken down into even smaller particles. In the early 20th century, the discovery of subatomic particles, protons, neutrons, and electrons, showed that atoms were not indivisible after all. These subatomic components opened the door to a whole new field of physics, quantum mechanics. Quantum mechanics offered a radically different view of reality. At the atomic level, particles behave in ways that defy the rules of classical physics. Electrons don't just revolve around the nucleus in neat, predictable trajectories. Instead, they exist as probabilities. Their location not fixed until they are observed. This strange behavior introduces the concept of superposition. Particles can exist in multiple states simultaneously until they're measured. At this level, the very nature of reality itself becomes uncertain. Classical physics taught us that the universe works like a precise machine with predictable cause and effect relationships. But quantum mechanics has shown that reality, at its core, is governed by probabilities. This new understanding challenged the notion of a solid, deterministic universe and replaced it with one in which randomness and uncertainty reign. So, as our understanding of the atom deepened, it became clear that even protons and neutrons, the components of the atomic nucleus, are not the most fundamental units of matter. Within these particles, scientists have discovered quarks, elementary particles that come together in certain combinations to form protons and neutrons. Alongside them were particles called gluons, which are responsible for binding quarks together, acting as mediators of the strong force, the fundamental interaction that holds the atomic nucleus together. Quarks, however, are unlike anything else in the world of physics. They cannot exist individually, only in combinations, bound together by a strong force. This force is so powerful that trying to separate quarks results in more quarks. It is a strange and complex system that continues to challenge our understanding of the fundamental structure of matter. Subatomic physics, and especially the study of quarks and gluons, has pushed the boundaries of our knowledge, making it even more uncharted. Although the standard model of particle physics successfully explains many particles and forces in the universe, deeper questions remain. How do these particles interact at the most fundamental level? What are the true building blocks of reality? One of the boldest theories in the search for answers to these questions is string theory. This revolutionary idea suggests that the fundamental particles we observe, quarks, electrons, and others, are not point particles at all, but tiny one-dimensional strings. These strings vibrate at different frequencies, and their vibrations give rise to the different types of particles we observe. String theory is not limited to the redefinition of particles. It suggests that these strings exist not only in the familiar three dimensions of space and one dimension of time, but also in multiple dimensions, perhaps 10 or 11. These additional dimensions are beyond our immediate perception. They're coiled so tightly that they remain hidden from view. If string theory is correct, then reality may be far more intricate than we ever imagined, and extend into realms we've yet to observe. And this brings us to Copenhagen interpretation, one of the most famous philosophical foundations for understanding quantum mechanics. Proposed by physicist Niels Bohr, this interpretation is based on the idea that quantum particles do not possess certain properties until they are measured. Before observation, they exist only as probabilities. It's the act of measurement, the interaction with a conscious observer, that gives rise to reality. In other words, until you observe a particle, its state is fundamentally undefined, neither here nor there. However, not all physicists are satisfied with the Copenhagen interpretation. Some prefer the more radical, many worlds theory, first proposed by Hugh Everett. According to this interpretation, every time a quantum event occurs, every time a particle's wave function collapses, the universe splits. In one universe, the particle follows one path. In another, it follows a different path. Instead of converging to one outcome, all possible outcomes occur, but in different branching universes. These parallel worlds exist simultaneously, each representing a different version of reality. The theory of multiple worlds provides an alternative to the idea that observation leads to a so-called collapse of reality. Instead, it argues that all possible realities exist, but we're only aware of the one we live in. This is a striking concept. It expands the imagination and makes us think that reality is much more layered than we see in everyday life. Whether we adhere to the Copenhagen interpretation, the many worlds theory, or some other explanation, one thing is clear. At the quantum level, the rules of reality are not at all what they seem. Despite its elegance, however, string theory remains largely unproven. The theory operates on such small scales that modern technology can't yet test its predictions. Even with all of our advances in subatomic physics, there is still much we do not know. Quantum mechanics and general relativity, the two pillars of modern physics, are still incompatible with each other, especially when it comes to explaining gravity on the smallest scales. While the Standard Model describes known particles and forces, it fails to account for dark matter, dark energy, and a complete explanation of gravity, suggesting that there's much more to reality than we can perceive or measure. So the question arises, where are you now? Not in the physical sense or location, but in the sense of experience. Your consciousness is the lens through which reality is perceived. But what exactly is consciousness? Is it simply the result of electrical signals and chemical reactions in the brain? Or is it something more? A fundamental part of reality itself? For much of modern science, consciousness has been understood as a byproduct of the brain, an emergent property arising from the complexity of neurological processes. Billions of neurons working in concert to form complex networks generate everything we feel, think, and perceive. From this perspective, consciousness is simply what happens when the brain reaches a certain level of complexity. But this explanation does not fully solve the mystery. The hard problem of consciousness is how philosopher David Chambers put it, is the question of how and why subjective experience, a sense of awareness, arises from purely physical processes. Why should a particular arrangement of neurons produce a vivid inner world of visual images, sounds, emotions, and thoughts? The gap between the physical workings of the brain and the richness of conscious experience remains one of the most confusing questions in science and philosophy. Some argue that consciousness is not just a byproduct of matter, but something much more fundamental. Some theories suggest that consciousness may be woven into the very fabric of reality, much like space and time. This idea, known as panpsychism, asserts that consciousness is not limited to humans or animals, but is a basic property of all matter, pervading the universe to some degree. So, if consciousness is fundamental, it could mean that the universe itself has consciousness to some extent. This shifts the question from how does the brain produce consciousness to how does consciousness manifest itself through matter? This in turn suggests that the distinction between mind and matter may be artificial, that consciousness and the material world are deeply interconnected. Other theories offer a more traditional approach. Consciousness is an emergent property. According to this view, the complexity of the brain creates consciousness in the same way that water emerges from individual hydrogen and oxygen molecules. In this view, consciousness is completely dependent on the physical structure of the brain. When the brain ceases to function, consciousness disappears. But this explanation still leaves unanswered the fundamental riddle of subjective experience. Philosophers and scientists have debated the true nature of consciousness for centuries. Is it reducible to material processes? Or is it something more, something that perhaps eludes our current understanding of physics and biology? If consciousness plays a role in shaping what we perceive as reality, could it be that our subjective experience is not just a reflection of reality, but part of its very foundation? Ultimately, the nature of consciousness remains one of the greatest mysteries. What is it about consciousness that distinguishes it from everything else in the universe? Is consciousness a window into a deeper level of reality, or just a byproduct of complex physical systems? The question of where you are, where consciousness fits into the grand plot of existence, remains an open question. The more we learn about the brain and the universe, the clearer it becomes that reality may be far more intricate than we can currently comprehend. Perhaps one day, discoveries will show that consciousness is not just something happening inside reality, but a fundamental key to understanding reality itself. Imagine a canvas of moments woven with the threads of time. Matter that stretches endlessly in all directions, capturing every choice, every event, every heartbeat. What if you could navigate this intricate fabric? What if you could go back in time, look into the future, or even change the course of history? Time, it governs our lives, but it remains one of the most mysterious phenomena in the universe. We measure it, we chase it, but can we control it? The concept of time travel has intrigued humanity for generations, inspiring countless works of fiction and sparking rigorous debate. But what can science say? Can time travel ever move from the pages of science fiction to the annals of scientific fact? Einstein's theory of relativity opened the door to this possibility by suggesting that time is not a constant, but a variable that can be manipulated. In addition, there are black holes, cosmic phenomena so powerful that they can distort not only light, but time itself. Did you know that astronauts aboard the International Space Station age slower than humans on Earth, even if only by a fraction of a second? This is not science fiction. It is a proven consequence of traveling at high speeds. So let us journey through the corridors of time. We'll explore the science, paradoxes, and limitless possibilities that may one day make time travel a reality. Welcome to a journey through time. Long before the advent of science as we know it, humankind was fascinated by the heavens and the passage of time. Ancient civilizations paid attention to the stars, sun, and moon, creating elaborate calendars and methods of measuring time. Transported to the modern era, this fascination has found a new canvas: film and literature. The concept of time travel has been a recurring theme, offering both escapism and a platform for intellectual curiosity. In 1895, H.G. Wells wrote the novel The Time Machine, which, by the way, not only popularized the term time machine, but also introduced the idea that time could be navigated like the dimensions of space. Then came Back to the Future, a pop culture powerhouse that took the concept of time travel and made it accessible to a whole new generation. Who could forget the DeLorean, the magnetic condenser, the flux capacitor, and Doc Brown's charming eccentricity? But it's not just a Western phenomenon. The allure of time travel knows no cultural or linguistic boundaries. From the Japanese Steins Gate to the Soviet Ivan Vasilievich changes profession, the theme of time travel resonates around the world. So what is it that attracts storytellers to this concept? The allure of rewriting history? The excitement of the unknown? Or perhaps the philosophical questions such journeys raise? It's a desire fueled by a mixture of nostalgia and anticipation, a longing to revisit cherished memories or leap into the promises of tomorrow. And as we stand on the cusp of scientific discoveries that could turn dreams into reality, the question becomes more important than ever. Could we? Should we? And what if we did travel through time? The blackboard is the canvas on which the abstract becomes possible. Here, equations like E equals mc squared are not just symbols. They're keys to understanding the universe. But can they unlock the secrets of time travel? From silver screens to living room TVs, time travel has been portrayed in countless ways. But let's peel back the layers of fiction and delve into the science that can make time travel more than just a plot device. Meet SpaceTime, the four-dimensional fabric of our universe. According to Einstein's theory of relativity, this fabric can be bent and deformed by mass and energy. But can it be torn or twisted to create a path through time? time dilation, a consequence of Einstein's theory, suggests that time can flow at different rates depending on the speed of motion or the gravitational field. For example, astronauts on the International Space Station age slightly slower than people on Earth. Experiments with particle gas pedals and atomic clocks have provided empirical evidence of time dilation. It's been observed that particles traveling near the speed of light decay more slowly than their stationary counterparts. In addition, there are wormholes, hypothetical tunnels in space-time that could theoretically allow time and space to be shortened. Although somewhat speculative, the math suggests that they are possible. Leading physicists and cosmologists have voiced their opinions on the matter, offering theories that range from plausible to downright bizarre. Some even suggested quantum mechanics, the science of the very small, may play a role in making time travel possible. And let's not forget black holes, the mysterious titans of space. Their enormous gravity is so strong that it distorts not only space but time itself. Could these cosmic phenomena be a gateway to other times? The scientific community is far from consensus. Time travel raises questions that challenge the very foundations of physics, from the nature of reality to the concept of causality. They say time goes forward, always forward, and never backward. But what if we could leap forward, skipping years, decades, or even centuries? The idea might not be as far-fetched as it seems. When it comes to slowing down time, speed becomes the main parameter. According to Einstein's theory of relativity, the faster you move in space, the slower you move in time. So, could extreme speed be our ticket to the future? Believe it or not, time travel to the future has already been done, albeit on a minuscule scale. Astronauts aboard the International Space Station experience time dilation and age a little slower than their counterparts on Earth. Let's turn our attention to the twin paradox, the famous thought experiment that takes time dilation to a new level. Imagine twins separated at birth. One travels through space at near light speed, while the other remains on Earth. Upon reunion, the space twin will appear younger. Achieving speeds close to the speed of light would greatly enhance this effect. However, such speeds are currently beyond the reach of our technology. Not to mention the energy requirements would be astronomical. Scientists and engineers are wrestling with these problems, researching propulsion technologies that could, one day, make near light speed travel possible. But even then, can the human body withstand such a journey? Imagine a future where time dilation capsules are as common as airplanes, allowing people to jump into the future to glimpse advanced civilizations or even avoid catastrophes. Will knowledge of the future be a gift or a curse? And what will it mean for the concept of free will? From science fiction to science articles, wormholes have captured our collective imagination. These hypothetical tunnels in the fabric of space-time may turn out to be the cosmic shortcuts we've been dreaming of. But what are wormholes, and could they be the key to time travel? Imagine folding a piece of paper so that 2 points touch, and then poking it with a pencil. In space-time, the wormhole would be that pencil, creating a straight path between 2 distant points. This concept gained traction in the scientific community thanks in part to Carl Sagan. While writing his novel Contact, he consulted with physicist Kip Thorne to explore the scientific possibility of using a wormhole for interstellar travel. Today, physicists are delving deeper into the math of wormholes. While the general theory of relativity allows for their existence, the equations also assume that they collapse too quickly for anything to pass through them. Theoretically, by introducing some exotic matter, for example, it could counteract the gravitational forces causing the wormhole to collapse, keeping it open long enough for something or someone to pass through. The portrayal of wormholes in popular media often glosses over these complexities. They're usually portrayed as stable, luminous vortices. But the reality, if they exist, can be much more volatile and unpredictable. Despite the lack of empirical data, the study of wormholes is a dynamic area of research. Scientists use computer modeling and indirect observations to understand their properties and potential uses. Imagine the possibilities if wormholes could be used for time travel. One end could be anchored in the present, the other in the future, or the past. The implications for research and even for preventing global catastrophes are staggering. Wormholes open the door to questions not only about where we might go, but when. And as we approach the potential discovery of these cosmic shortcuts, we must ask ourselves, are we ready for the responsibility associated with such power? In the world of the very small, where particles are also waves, and reality itself seems blurred, lies the quantum world. Could this region of uncertainty hold the keys to unlocking time travel? Quantum mechanics challenges our everyday understanding of the world. Take the two-slit experiment, in which particles behave as both particles and waves. This duality suggests that, at the quantum level, the fabric of reality is much more malleable than we thought. Great minds like Richard Feynman and Niels Bohr have delved into the mysterious world of quantum mechanics, a theory that's been incredibly successful in explaining the behavior of matter and energy at extremely small scales. Some physicists suggest that quantum mechanics may offer a basis for time travel. Quantum tunneling, for example, allows particles to pass through barriers as if they're ghosting through walls in the two-slit example. Can a similar principle enable time tunneling? Quantum computing is a new field that uses the principles of quantum mechanics to perform calculations at speeds unimaginable to classical computers. Some speculate that quantum algorithms could solve equations related to time travel that are currently too complex for today's computing machines. The concept of quantum entanglement adds interest. Imagine two particles cooked together in a certain way. Once entangled, these particles become interconnected, forming a single quantum system. The truly stunning aspect of entanglement is that the state of one particle instantly affects its entangled partner, regardless of the distance separating them. This could be across the room or even across the galaxy. Change the spin of one, and the other instantly changes. Albert Einstein famously called it spooky action at a distance. At first, he didn't like this idea because it seemed to violate the limit of the speed of light set by his theory of relativity. Since then, however, numerous experiments have confirmed that entanglement is a real and fundamental aspect of quantum mechanics. Could such an effect at a distance make a difference to instantaneous time travel? While the intersection of quantum mechanics and time travel is still in the realm of speculation, it is a hotbed of scientific research. Researchers are studying everything from quantum loops in time to the role of quantum gravity in the early universe. Imagine a future in which the principles of quantum superposition could account for multiple timelines or realities. What if you could exist in a superposition of past and present? Could quantum mechanics be the final piece of the puzzle in our quest to conquer time? Moving on, let's move from the world of the microscopic scale to the grandiosely large one, black holes, mysterious titans of space whose gravity is so strong that not even light can leave them. But could these celestial phenomena hold the secret to time travel? Enter the concept of closed time-like curves. A closed time-like curve, or CTC, is a path in spacetime that loops back on itself. Theoretically, an object or even a person traveling along a CTC could end up in an earlier point in time. The idea was first proposed by physicist Kurt Gödel in 1949. Gödel's solution to Einstein's field equations suggested that rotating universes could contain paths looped in time. However, these solutions required certain conditions, such as a universe filled with rotating matter. Although Gödel's model is considered physically implausible in most cases, it has opened the door for other scientists to explore the concept. The main challenge is to find a scenario in which STSSs could exist without violating the laws of physics. One such scenario involves rotating black holes, known as Kerr black holes. Massive gravitational and rotational forces can theoretically twist space-time into loops, creating CTCs. But there's a catch. Most models predict that the center of a rotating black hole, known as a singularity, will be ring-shaped rather than point-shaped. This ring feature could potentially serve as a gateway to the CTC. However, powerful gravitational forces could also create a barrier known as the Cauchy horizon, beyond which the laws of physics are violated. The study of CTCs and black holes is fraught with paradoxes and uncertainties. For example, if CTCs exist, they can lead to paradoxes in which cause and effect are reversed. This has prompted some physicists to propose the chronology defense hypothesis, which suggests that the laws of physics prevent such paradoxes. Imagine the possibilities and dangers of approaching a rotating black hole. Would we ever be able to navigate safely through such a treacherous region of space-time? And if we could, what would we find on the other side? Another universe? Another time? In addition to black holes and closed time-like curves, there's another cosmic mystery that could potentially open a path through time: cosmic strings. These hypothetical one-dimensional cracks in the universe may be remnants of the Big Bang itself. Cosmic strings are thought to have formed in the early moments of the universe as they cooled down after the hot and dense state of the Big Bang. These strings would have been thinner than an atom, but incredibly dense, and would have had a tremendous gravitational pull. Although still theoretical, cosmic strings offer intriguing possibilities for time travel. Physicists J. Richard Gott and William Hiscock have made significant contributions to our understanding of these mysterious objects. Gott suggested that a cosmic string traveling at the speed of light could theoretically distort spacetime enough to create a loop allowing time travel into the past or future. However, the existence of cosmic strings is still a matter of debate. Their detection would require astronomical observations on scales that are currently beyond our capabilities. Moreover, if they do exist, harnessing their power for time travel would be a challenge. Now, let us return to quantum entanglement. We've already explored how entangled particles are connected in ways that transcend ordinary spatial distances. Can they be bound in time? Some theories suggest that entangled particles can be used to transmit information not only in space, but also in time. Imagine a future in which quantum entanglement is used to create a kind of quantum internet that allows instant communication across eras. The intersection of cosmic strings and quantum entanglement is a frontier of theoretical physics rife with unanswered questions and untapped potential. Researchers are exploring how the two phenomena might be connected and what this might mean for our understanding of time travel. Imagine a scenario in which cosmic strings are manipulated at the quantum level through entanglement. This would represent a merger of the very large and the very small, a meeting point of cosmic and quantum scales that could revolutionize our concept of time travel. As we venture into the realm of time travel, we face many paradoxes and riddles. These are not just intellectual exercises. They are fundamental questions that can make or break the possibility of time travel. First of all, this is the grandparent paradox. Imagine going back in time and not allowing your grandparents to meet. If they never meet, one of your parents will never be born, and therefore neither will you. But if you were never born, how would you even be able to travel through time? The grandfather paradox raises questions about causality and the nature of time itself. Some theorists suggest that such paradoxes can be resolved through the existence of parallel universes, where each solution generates a new timeline. Another confounding bootstrap paradox is named after the popular expression, pulling yourself up by your bootstraps. Imagine going back in time to give Shakespeare a copy of your works, which he then claims as his own. Where, in that case, did these works originate? The bootstrap paradox creates a closed loop of cause and effect with no apparent origin. It challenges our linear understanding of time and suggests that cause and effect may not be as simple as we think. Another paradox, the paradox of predestination, is when a time traveler's actions in the past lead to the very event he was trying to prevent. This raises questions about free will and determinism, and whether we can ever really change the course of history. The study of time travel paradoxes is not just a playground for philosophers. It's a serious area of research in physics and metaphysics. The resolution of these paradoxes may shed light on time travel. While we stand on the threshold of scientific discovery, the future of time travel remains a mystery shrouded in paradoxes, theories, and cosmic phenomena. What was once the realm of science fiction is gradually approaching the realm of real science. From cosmic strings to quantum entanglement, from spinning black holes to closed time-like curves, we explore the theories and possibilities that could one day make time travel a reality. Current research is paving the way for new experiments, new technologies, and perhaps even a new understanding of the structure of reality. But as we teeter on the edge of cosmic horizons, one question becomes more important than all others. Are we ready for what we might find? Time waits for no one, but what if we could wait for time? What lies beyond the observable universe? As we gaze into the celestial tapestry, our understanding stretches from the familiar glow of our solar system to the enigmatic dark spaces that challenge every truth we hold dear. From the rudimentary lenses of Galileo, which first charted the moons of Jupiter, to the intricate orbits of modern space telescopes capturing distant galaxies, our tools for probing the cosmos have evolved dramatically. Yet each discovery peels back only a layer of more profound mysteries ahead. The intriguing presence of dark matter and dark energy suggests that much of the universe is shaped by substances and invisible forces, dictating the speed at which galaxies rotate and the universe expands. But could there be more than our universe? The theory of the multiverse proposes a spectrum of possibilities where different laws of physics may apply. Each discovery, from black holes bending the fabric of space-time to gravitational waves echoing through the cosmos, is a puzzle in understanding the broader cosmic picture. These cosmic phenomena challenge our perceptions and invite us to contemplate the more profound mysteries that define our universe and possibly others. Are we ready to redefine our understanding of the cosmos and accept the boundless realms of the multiverse? This narrative challenges our perceptions and invites us to explore the profound implications of what lies beyond the observable universe. As humankind has plumbed the depths of the universe, it's begun to encounter phenomena that our traditional understanding of physics could not describe. Among them are dark matter and dark energy, components of the cosmos that remain invisible to our telescopes, but profoundly affect the structure and fate of the universe. The mystery of dark matter first arose from the study of the rotation curves of galaxies. According to Newtonian mechanics, stars at the galaxy's outer edges should rotate slower than in the center, like the planets in our solar system. However, observations have shown that this is not the case. Instead, the rotation rate of stars and galaxies remains constant, suggesting that there is an invisible mass exerting an additional gravitational force. This matter, detectable only through its gravitational influence, forms the entire skeleton of the universe. Turning our gaze from the hidden mass inside galaxies, we encountered an even more elusive component: dark energy. This mysterious force drives the universe's accelerating expansion, a phenomenon first detected by the strange behavior of distant supernovae. Instead of slowing down, as one might expect from the gravitational pull of the entire universe's mass, its expansion is accelerating. Among these expansive forces, black holes anchor the cosmic drama. Born from the collapsing cores of massive stars, these gravitational giants warp space-time to the point where even light cannot escape their grip. The first direct image of a black hole's event horizon revealed a universe stranger and more fantastic than we could have imagined. And rather than providing new answers, it only added questions to those already existing. However, the interaction of these cosmic giants is not silent. When black holes merge, they send gravitational waves throughout the universe, rips in space-time that we've only recently begun to detect. Observatories like LIGO and Virgo are capturing these waves, giving us new insights into some of the most violent events in the universe. Gravitational waves have opened a new channel through which we can explore the cosmos, complementing the electromagnetic spectrum that's been our primary window into the universe. By analyzing these waves, scientists can unlock the secrets of black hole masses, rotations, and merger details, enriching our understanding of the fundamental physics that governs the most extreme objects in the universe. But this is only part of humanity's quest to understand the cosmos's cruel mechanisms and find potential cradles for life throughout the universe. The search for exoplanets and the search for extraterrestrial intelligence represent two journeys into the unknown, guided by our deep curiosity about the cosmos. The discovery of myriad worlds orbiting stars within our galaxy has opened a new chapter in our understanding of the universe, expanding our horizons beyond our solar system to include many planets with conditions as diverse as those on Earth. Each discovery, from the sultry surfaces of hot Jupiters to the potentially habitable conditions on super-Earths, becomes the basis for a broader story about our place in the universe. With its unprecedented observational capabilities, the James Webb Space Telescope allows us to peer into the atmospheres of these distant worlds, analyze their composition, and look for signs of life. This bridge to the stars is not just about discovering new planets. It's about understanding the conditions that can support life, a question that naturally extends to the search for signals from civilizations beyond our planet. Meanwhile, an initiative known as the Search for Extraterrestrial Intelligence, or SETI, has continued for decades to explore the silent expanse of space, listening for faint whispers of civilizations that may exist in these distant worlds. Use of technologies covering a vast electromagnetic spectrum, SETI's efforts underscore the enormity of our search and the tantalizing possibility that we are not alone. At the heart of SETI's theoretical foundation is the Drake equation. Formulated by astronomer Frank Drake in 1961, the equation offers a way to estimate the number of active, friendly, extraterrestrial civilizations in the Milky Way galaxy. The equation considers factors such as the star formation rate, the fraction of stars with planetary systems, the number of planets on which ecosystems can develop, and the likelihood of intelligent life. The equation highlights the vast number of unknowns in this search, from the fraction of habitable planets with life to technological civilizations' longevity. Nevertheless, searching for the potential for life in space is only the beginning. The deeper we delve into the mysteries of the cosmos, the more our knowledge expands, and the more questions arise. The constant change in our understanding of the cosmos lays the groundwork for considering even more possibilities. The enigmatic phenomena discovered in the course of these investigations, the invisible scaffolding of dark matter, and the pressure of dark energy on the expansion of the universe, provide the basis for considering the multiverse not as science fiction, but as a plausible structure that can explain mysteries that remain beyond our current scientific reach. Our current search, limited to the observable universe and based on our understanding of life on Earth, can only scratch the surface of what's truly possible. Multiverse theory opens up an even more comprehensive range of possibilities, reaching beyond our observable universe into realms where the fundamental laws of physics may be radically different. The Drake equation, which is the basis for our search for extraterrestrial intelligence by estimating the number of friendly civilizations in our galaxy, operates within the physical laws of our universe. However, if we embrace the multiverse theory, the equation may be just one of countless ways to understand the potential for life in a more extensive and diverse multiverse landscape. In general, the multiverse concept pushes the boundaries of our cosmic understanding into new uncharted territories. It suggests that our universe, as vast and complex as it is, may be only one of a vast number, perhaps an infinite number, of universes existing parallel to our own. The seeds of the multiverse theory are in quantum mechanics and cosmology. With its probabilistic nature, quantum mechanics introduces the idea of parallel outcomes arising from the same quantum events. If we apply this principle to cosmological scales, we can assume that in the universe, each possibility is realized in its own separate cosmos. Cosmic inflation, a theory describing the exponential expansion of the early universe, provides another basis for a multiverse. Inflation suggests that bubbles of space may have formed, each expanding into its universe with a larger multiverse. These bubbles may have different properties and physical laws dictated by the nature of the inflationary field in each region. Most conceptions of the multiverse are not monolithic. They include several models, each with its implications for our understanding of reality. Bubble universes emerging from the theory of cosmic inflation. Bubble universes are distinct regions within a large space, each having undergone its inflationary expansion. These universes can radically differ from our own, with different physical constants and laws. Quantum multiverses, based on quantum mechanics. This interpretation asserts that each quantum decision point generates a new parallel universe. Every conceivable outcome of any event generates its universe, resulting in an almost unimaginable variety of parallel histories and futures. Mathematical universes. This model assumes the existence of all mathematically possible universes. If physical laws, as we understand them, are merely mathematical structures, then all structures that can be described mathematically exist as tangibly as our universe. For example, let's look at the type of multiverse classified by astrophysicist and cosmologist Max Tegmark. Level 1. The Infinite Universe. At the first level of the Tegmark model, the universe extends infinitely beyond the observed cosmos. At this level, it's assumed that our observable universe, 92 billion light-years in diameter, is just an infinitesimal particle in an increasingly vast cosmic landscape. Every structure, event, and variation is infinitely repeatable in space, suggesting that our duplicates exist somewhere in similar conditions, if not identical. Level 2. The Post-Inflationary Multiverse. The second level of Max Tegmark's multiverse model explores the realm where individual universes arise from their own unique Big Bang events. This classification is rooted in the concept of chaotic inflation, which assumes the existence of a cosmos in which our universe is just one of countless others, generated by inflationary bubbles. Chaotic inflation assumes that the rapid expansion of the universe, which we think of as the Big Bang, is not a single event, but a common phenomenon throughout cosmic history. In this model, inflation never stops completely. It stops only locally, like bubbles forming and separating in boiling water. Each bubble becomes a new universe with potentially different physical constants. In these individual universes, the fundamental constants and even the laws of physics can change from bubble to bubble. These differences can lead to universes that are radically different from our own. For example, gravity may be stronger in one universe, affecting the formation and evolution of stars and galaxies. In another, different levels of electromagnetic forces may change the chemistry of life, of course, if life is even possible in it. To understand the implications of changing these constants, imagine throwing a ball in a universe where gravity is 3 times stronger than it is here. The ball would not fly as far or as high, fundamentally changing games like basketball or soccer. If you extend this analogy to celestial mechanics, you can imagine that planets could orbit much closer to their stars, and stars could be smaller and burn up faster. If physical constants can vary so widely, then the conditions that led to the emergence of life on Earth are just one possibility of a vast cosmic lottery. Each universe may be a unique experiment to explore the possibilities of physical reality. Although second-level multiverses differ fundamentally in their constants, They share a common link with their first-level multiverses, where all the laws of physics are constant, but the initial constants vary. This multi-level structure of the multiverse not only expands our understanding of what's possible, but also provides a basis for understanding the incredible variety of conditions under which universes can form. Level 3. The Many Worlds Interpretation of Quantum Mechanics. Perhaps the most disconcerting of Tegmart's levels, the third level, introduces the concept of quantum mechanics into the multiverse theory. According to the interpretation of multiple worlds, every possible outcome of every event defines or gives rise to a new world or universe. This level assumes infinite timelines and possibilities where each conceivable scenario takes place in its own universe. Imagine a simple everyday decision, such as turning left or right on your way to work. In the Many Worlds interpretation, each choice results in a branching universe. One version of you turns left, while another version turns right in a parallel universe. These universes exist simultaneously, but do not interact with each other, and each follows its path of reality based on that single quantum decision. Another example is the flip of a coin. In our everyday experience, the coin falls either heads or tails. However, in the context of the Many Worlds interpretation, at the moment of the coin flip, the universe is split into two. One where the coin falls heads and one where it falls tails. Each outcome exists in its separate universe. And the consequences of this simple event spread outward, affecting further events in each respective universe. However, this interpretation goes beyond human-scale events and encompasses all quantum events in the universe. For example, the same decay of a radioactive atom, a fundamentally random process at the quantum level, would cause the universe to split into one in which the atom decayed and one in which it did not. Each of these universes would continue to evolve independently, accumulating its unique history. The fascinating aspect of this level of the multiverse lies not only in its scientific implications, but also in the way it reflects the complexity of human choices and the inherent unpredictability of life. Just as we can ponder what-if scenarios regarding our past decisions, the interpretation of many worlds realizes these alternatives in countless parallel universes. Level 4. Ultimate Ensemble. The fourth level of Max Tegmart's multiverse classification represents the most radical and profound conception of all possible universes. In this model, known as the mathematical universe hypothesis, reality is viewed as a landscape of mathematical structures. Each structure defines a separate universe, distinguished not only by physical constants or laws, but also by potentially entire mathematical structures. According to the hypothesis of mathematical universes, our physical world is not just described by mathematics, it is mathematics. This means every conceivable mathematical structure exists as a physical reality somewhere in a multiverse. These universes may function based on entirely different mathematical rules than the ones we know and understand. To illustrate this profound concept, let's take a simple object like an orange. Imagine holding an orange in your hand. It's familiar and tangible, but this orange is a set of mathematical properties at its core. The shape of the orange, the ideal sphere, is not just a physical form, but a geometric expression that describes contours and volume, defining how the orange exists in space. Now, think about the orange color that we see. This bright hue is not just a random feature. It results from light interacting with molecules on the orange's surface that absorb and reflect light at specific wavelengths. Because the science of light, optics, is deeply mathematical, it relies on equations that describe how light behaves when it encounters an object. Even the taste of an orange, the combination of sweetness and acidity, is driven by chemical reactions that can be quantified and predicted with mathematical precision. The concentrations of sugars and acids are subject to chemical laws, essentially mathematical relationships that determine how substances interact. Every aspect of an orange, from its growth to the sensations it evokes when we eat it, can be described using math. In this way, this simple fruit becomes a small, tangible proof of a much larger truth. Our entire universe, from the smallest atom to the largest galaxy, can be part of a grand mathematical structure. If we accept that every mathematical structure corresponds to a physical universe, the implications for science and philosophy are enormous. It implies that any universe that a consistent set of mathematical rules can describe exists as surely as our own. It implies that universes with radically different properties that defy our physical intuition are just as real as our own. Consider a universe in which the dimensions of space and time are not 4, as in our visible universe, but 5, 10, or even more. The behavior of particles and forces in such a universe could be radically different, changing the process of matter formation and evolution. Or imagine a universe governed by a different type of geometry, where the shortest path between 2 points is not a straight line, but some other curve, which radically changes the structure of the universe and the life it can support. Level 4 is connected to the other levels of the multiverse, providing the ultimate framework, while levels 1 to 3 deal with the universes that differ in initial conditions, physical constants, or quantum results. Level 4 encompasses all possible mathematical realities. It offers a cosmos where the boundaries of possibility are limited only by the limits of the mathematical imagination. The implications of the multiverse theory go beyond physics and into philosophy, forcing us to think about the most fundamental concepts of reality, causality, and existence. If the multiverse is real, it means that with all its complexity and beauty, our universe is just one of countless others, each with its own history, laws, and perhaps even life forms. In the scientific realm, the multiverse theory raises profound questions about the nature of scientific inquiry and evidence. Since other universes in the multiverse are, by definition, beyond our observation, the theory walks a fine line between physics and metaphysics, forcing us to reflect on views of the principles of empirical science.
That's one small step for man, one giant leap for man.
As we ponder the vastness of the universe and the possibility of countless worlds in the multiverse, our quest for space exploration continues to propel us forward. The next chapter in human space exploration is being written now, with ambitious programs and missions that aim to expand our presence beyond Earth, back to the Moon, onward toward Mars, and eventually beyond our solar system. In conjunction with international and commercial partners, NASA's Artemis program marks a major milestone in our efforts to explore the Moon. Named after Apollo's twin sister, the Artemis program aims to return humans to the Moon by the mid-2020s, with the lofty goal of a sustained human presence there by decade's end. Unlike the Apollo missions, which were short-term visits, Artemis envisions a long-term presence of humans and robots on the Moon, utilizing its resources and using it as a testing ground for technologies needed for deeper space exploration. The Artemis architecture includes Gateway, an orbital lunar outpost that will support long-term human missions to the Moon and serve as a transfer point for missions to Mars and beyond. Gateway will facilitate scientific research, provide a platform for testing new technologies, and usher in a new era of the international cooperation in space. In turn, the red planet Mars has long captured our imagination as the next frontier for human exploration. Based on decades of robotic exploration, plans for manned missions to Mars are taking shape to send astronauts to Mars in the 2030s. These missions will require improvements in life support, propulsion, and habitat technologies, and a better understanding of the psychological and physiological effects of long-duration space travel. Human missions to Mars will aim not only to answer fundamental questions about the planet's history and geology, but also to search for signs of past life, test the possibility of existence on Martian soil, and lay the groundwork for future colonization. While the Moon and Mars are within our reach, the ultimate challenge is interstellar travel, expeditions to other star systems. One of the most visionary projects in this area is Breakthrough Starshot, an initiative to build a fleet of light-sail spaceships capable of traveling to our nearest stellar neighbors, such as the Alpha Centauri system. These spacecraft could theoretically be accelerated to a significant fraction of the speed of light, allowing them to reach Alpha Centauri in just over 2 decades after launch. Such missions could provide invaluable data on other star systems and potentially habitable exoplanets, paving the way for future interstellar exploration. The journey to the Moon, Mars, and ultimately to the stars is not just a series of missions, but a continuation of our fundamental quest to explore, to understand, and connect with the universe around us. Even stepping into the next chapter of human space exploration can push the boundaries of our technological and scientific capabilities and inspire future generations to dream of the possibilities that lie beyond our cosmic horizon. Imagine a line, a simple, unbroken line stretching into infinity. This line, in its purest form, represents the first dimension, a realm of length but without depth, a universe infinitely long but impossibly thin. Now, let's broaden our perspective, introduce a second line intersecting the first, and suddenly we're in the realm of the second dimension, a plane where length and width interact in harmony, but depth remains a variable alien to them. As we go one step higher, we find ourselves in the familiar embrace of the third dimension. This is where depth comes in, adding volume and substance to our world. Buildings rise, valleys deepen, and the universe takes on texture and shape. But what if we could add another layer? Time is the elusive fourth dimension that permeates our three-dimensional space. Invisible but omnipresent, it dictates the rhythm of our lives, a continuous thread connecting each previous moment with the current one and the current one with the next. In this realm, our understanding of reality becomes more complex and broader. Here, the very fabric of the universe reveals its complexity, hinting at dimensions beyond our sensory perception. However, nature hints at even more complex dimensions. In the field of physics, theories suggest the existence of dimensions beyond our perception, necessary for the fundamental forces that govern the universe. These higher dimensions, although beyond our sensory perception, are crucial to understanding the structure of the cosmos. Join us as we try to unravel their mysteries together today, one dimension at a time. In a historical context, the concept of measurement permeates all human thought, from the abstract reflections of ancient philosophers to the revolutionary discoveries of modern physics. Philosophers once pondered the nature of existence, laying the foundations for our understanding of space. In their discussions, they questioned the very essence of reality, imagining realms beyond the tangible. As the centuries passed, these philosophical speculations paved the way for more structured inquiry into the nature of the universe. Meet the visionary Hermann Minkowski, who irrevocably changed our understanding by proposing that time and space are not separate entities, but intertwined dimensions that form the fabric of space-time. Albert Einstein, in turn, based on the foundation laid by Minkowski, presented the revolutionary theory of general relativity, restructuring our understanding of gravity, space, and time in a single continuum, forever changing the course of physics. Thus, from the philosophical quest of the ancient thinkers to the scientific revolutions sparked by Minkowski and Einstein, the journey through the evolution of spatial thinking reveals a relentless quest to comprehend the true nature of our universe. So, over time, we've come to realize that to truly comprehend the fabric of our reality, we must go beyond the three tangible dimensions into the realm of the fourth dimension, time. The concept of time as a dimension is both profound and persuasive, defining our existence and the universe as a whole. Unlike the three spatial dimensions, time has a direction. It moves inexorably forward, from the past, through the present, and into the future. This unidirectional flow of time distinguishes it from space, bringing to the universe a temporal structure that is fundamental to our understanding of reality. To illustrate the importance of time as a dimension, consider a simple everyday scenario: organizing a meeting. When we suggest that someone meet at a certain place, we unconsciously navigate the three basic spatial dimensions to determine where. It makes sense that if we arrived at different places, no meeting would take place. However, the when, the dimension without which the meeting will not take place, is no less important. That is, coming with your friend to the same place but at different time intervals, you'll not be able to see each other. This intertwining of space and time is manifested in the concept of world line, the path that an object or person takes through space-time, thus representing its history and future. The idea of world lines provides a vivid illustration of how events are linked together in the fabric of space-time. For two people to meet, their world lines must intersect at a precise point in both space and time. This intersection is not just a spatial coordinate, but a space-time coordinate, the only point in the vast continuum of the universe where both where and when coincide. This principle applies not only to simple encounters but also to the fundamental workings of the cosmos. Celestial bodies from planets to stars trace their own world lines through space-time, their paths determined by the interplay of spatial positions and temporal moments. For example, the Earth's orbit around the Sun is not just a path through space, but a continuous journey through time, with each point in the orbit representing a unique moment. The integration of time as a dimension has a profound effect on our perception of the universe. It forces us to look beyond static images of space to the dynamic unfolding of events. Time allows us to understand the universe not as a set of individual moments, but as a continuous narrative where cause and effect bind our reality into a coherent whole. The inclusion of time as a dimension has catalyzed major advances in physics, particularly through Einstein's theories of relativity, which we've already mentioned. These theories not only deepened our understanding of the cosmos, but also paved the way for new research in quantum mechanics and cosmology. Einstein's revelation that time is relative, it slows down or shrinks depending on the velocity of an object, challenged the idea of a universal clock. This concept, rooted in the special theory of relativity, illustrates how the passage of time changes for observers in different reference frames. This phenomenon is confirmed by experiments, for example, with atomic clocks on fast-moving airplanes. In quantum mechanics, time as a dimension underlies the evolution of particle state governed by the Schrödinger equation. This basis is important for understanding phenomena such as entanglement and superposition, where the time dimension provides a probability distribution of outcomes. Going beyond the fourth dimension opens the door to a realm where our everyday experience and the laws of physics as we know them are fundamentally challenged and expanded. In search of a unified theory that harmonizes the principles of quantum mechanics and the general theory of relativity, physicists have ventured into the theoretical landscape of higher dimensions, where the fabric of the universe becomes even more intricate and mysterious. The fifth dimension and beyond are not just speculative constructs, but important components in the quest for a deeper understanding of the universe. In theories such as string theory, these higher dimensions offer solutions to some of physics' most challenging mysteries, including the unification of fundamental forces and the nature of gravity at quantum scales. The difficulty in visualizing higher dimensions is that our perception is inherently three-dimensional. Therefore, analogies become an invaluable tool. One of the classic analogies to help understand the concept of higher dimensions is to imagine the perspective of a two-dimensional being, often called a flatlander, living in a flat two-dimensional world. This being can move forward and backward, left and right, but has no concept of moving up and down because these dimensions do not exist in its two-dimensional experience. Imagine a three-dimensional sphere passing through this two-dimensional world. To a flatlander, the sphere would first appear as a dot when the sphere is just touching the two-dimensional plane, gradually increasing into a circle as more of the sphere passes through the plane, and then decreasing again to a point as the sphere leaves the plane, before disappearing altogether. A two-dimensional being would perceive this event as a circle that appears out of nowhere, changes size, and then disappears, without realizing what three-dimensional object is causing the phenomenon. String theory, the leading candidate for a unified theory, posits that particles are not the individual points we see them to be, but tiny vibrating strings, whose modes of vibration determine the properties of the particles. This theory requires the existence of more than 4 known dimensions. In fact, it suggests that there may be as many as 10 or 11. These additional dimensions are compacted or convolved so that they are imperceptible on our scale, like the sphere in the flatlander example. In the 5th dimension, we encounter a space containing all possible universes that start from the same initial conditions as our own universe. Imagine a tree, each branch representing a different decision or outcome leading to a different reality, all coming from the same trunk. Just as a person standing at the base of the tree can choose which branch to climb, a being with access to the 5th dimension can explore these alternate realities, each a variation of our own universe, but with slightly different outcomes. The ascent to the 6th dimension opens a plane containing all possible universes with the same initial conditions as ours, but with any possible set of laws of physics. If we think of each universe as a sheet of paper, the 6th dimension would be like a stack of such sheets, each representing a different universe. A being capable of traveling through the 6th dimension could hop between these universes, learning the different outcomes and laws governing each reality. The 7th dimension extends this concept to include universes that start from different initial conditions. To use a library analogy, each book represents a different universe. The 7th dimension encompasses the entire library, offering not just different stories, universes with the same initial conditions as ours but with different outcomes, but completely different genres, universes with different initial conditions. A 7-dimensional being could move through this library, experiencing an infinite number of universes, each with its own unique initial conditions and physical laws. In the 8th dimension, we find a web of all possible universes, each with its own initial conditions and laws of physics, as well as all possible variants of their development in time. Imagine a huge web where each thread represents the timeline of a separate universe, and each node where the threads cross represents an important event that could lead to the branching of new universes. The 8th dimension encompasses this entire web, allowing you to travel between any nodes, exploring the connections between different universes and their history. As we approach the 9th dimension, we encounter all possible laws of physics and initial conditions that have existed or will ever exist. This dimension can be compared to the art of origami, where a single piece of paper can be folded into numerous shapes. Each fold represents a change in the initial conditions or laws of the universe. And the 9th dimension includes all possible combinations of folds, resulting in all conceivable and inconceivable universes. A being living in the 9th dimension will not just have absolute freedom to cross the boundaries between all possible realms of reality, it will experience all existence and all its possible variations. The 10th dimension is the pinnacle of the hierarchy of dimensions, where all possible outcomes, realities, and existences converge. It's the space that encompasses all conceivable and inconceivable timelines for every conceivable universe, effectively encompassing all possibilities of existence and non-existence. This concept can be visualized as an infinitely complex branching tree or network, where each branch represents a different outcome or timeline. And all branches ultimately converge at one point, the 10th dimension. Visualizing the 10th dimension is challenging because of its abstract nature. One approach is to use the analogy of a tree, where each branch represents a different timeline or universe, and each leaf represents a possible outcome within that universe. Moving from trunk to leaves, we move from the initial conditions of a universe, lower dimensions, through the various choices and events, higher dimensions, that lead to all possible outcomes. The 10th dimension represents the point where all these possibilities come together, the singularity of infinite potential outcomes. It suggests a cosmos in which all possible outcomes not only can happen, but happen in some timeline or universe in the 10th dimension. The concept itself invites us to reflect on the vastness of possibilities that lie beyond our observable universe. It raises questions about fate, choice, and the underlying structure of the cosmos, prompting a broader exploration of potential realities that may exist beyond our immediate perception. The exploration of higher dimensions beyond our familiar three-dimensional space and fourth-dimensional time has profound implications for both physics and cosmology. Not only is this field of study designed to challenge our fundamental understanding of the universe, but it may also hold the key to uniting the disparate forces of nature, potentially solving some of cosmology's most enigmatic puzzles. Recognizing the existence of higher dimensions plays a key role in the search for a theory of everything, a single framework that will seamlessly unify general relativity and quantum mechanics. Currently, these two pillars of modern physics describe the cosmos on very different scales and in seemingly incompatible terms. General relativity perfectly explains the gravitational interaction of massive celestial bodies, while quantum mechanics reveals the intricate world of subatomic particles. Higher dimensions may also offer new insights into cosmological mysteries, such as dark matter, dark energy, and the nature of black holes. For example, some theories suggest that what we perceive as dark matter may be gravitational effects from matter in parallel branches, a concept from M-theory, which suggests multiple parallel membranes, or branes, as fundamental components of the universe, each potentially containing another universe in higher dimensions. Looking to the future in the field of energy, mastering the intricacies of higher dimensions could pave the way to harness forms and mechanisms of energy that we cannot now even imagine, and potentially lead to the creation of clean, virtually inexhaustible sources of energy. Similarly, the field of space travel could be revolutionized by a better understanding of the fabric of space-time, perhaps eventually enabling warp drives or other forms of faster-than-light travel. Concepts that are currently in the realm of science fiction but could be theoretically plausible within higher dimensions. The search for higher dimensions is already underway. Researchers are exploring the subatomic world with particle gas pedals such as the Large Hadron Collider at CERN, looking for evidence of additional dimensions and the particles that may inhabit them. This experimental work is complemented by theoretical studies that delve physicists and mathematicians into the abstract realms of high-dimensional spaces. as we complete our journey through the dimensions. From the simplicity of a line extending into infinity to the unfathomable complexity of the 10th dimension, we're faced with the inherent challenge of visualizing spaces beyond our three-dimensional experience. Through math, we can describe properties and relationships within higher dimensions, and physics offers theories such as string theory and M theory that hint at the existence of these additional dimensions. Animation such as tesseracts allows us to conceptualize high-dimensional shapes and their projections or shadows in lower dimensions. Further exploration of higher dimensions promises to revolutionize our understanding of the universe. Just as the transition from a flat Earth to a spherical Earth many centuries ago broadened humanity's horizons, this expanded perception has the potential to influence not only science, but also art, philosophy, and all aspects of human creativity, inviting us to rethink the cosmos and our place in it. What if the relentless forward march of time, the ticking of seconds, the changing of seasons, the aging of our bodies, is nothing more than a grand illusion? What if the past, present, and future, the cornerstones of our existence, don't truly exist in the way we believe? For centuries, these questions have haunted philosophers, scientists, and everyday minds alike. Is time woven into the very fabric of reality, or is it a stubbornly persistent trick our brains play on us? The deeper we delve into the mysteries of the cosmos, the more a tantalizing possibility emerges. What if our entire reality is a simulation? If so, could time simply be a programmed construct, a line of code within a vast, artificial universe? This concept forces us to question everything, even our most fundamental assumptions about the passage of moments. We often take time for granted, but it shares a surprising similarity with another constant in our lives: color. The colors we perceive are not inherent properties of objects themselves. Instead, they're creations of our brains as they interpret wavelengths of light. Could a similar process be happening with time? Perhaps our sense of temporal flow is a construct, a way for our minds to impose order and meaning on an otherwise timeless universe. Consider the vibrant world of color that surrounds us. A juicy red apple, a field of yellow sunflowers, clear blue of a summer sky. At first glance, these colors might seem like fixed properties of the objects themselves, yet the reality is far more complex. Colors don't exist independently in the world. They're born within our minds. Our eyes detect different wavelengths of light, and our brains translate those signals into the rich tapestry of hues that shape our visual experience. This process isn't merely about biology. People with different forms of color blindness perceive the world in distinct ways. Animals with different eye structures experience an even wider range of colors, some even seeing wavelengths invisible to us. What we call color is highly subjective, shaped by the unique capabilities of our sensory systems. Just as our perception of color is a creation of our minds, could the same be true of time? Perhaps the feeling of time ceaselessly flowing forward, the division of our lives into past, present, and future, is merely a way to make sense of change within the universe. Maybe, like color, time emerges from the interaction between our consciousness and a reality that may be fundamentally timeless. The idea that time may be an illusion isn't new. From ancient philosophers grappling with the nature of change to modern physicists unraveling the fabric of space-time, the question of time has persistently challenged our understanding. Today, we're going to delve into this enigma, exploring the scientific discoveries and philosophical riddles that hint at the possibility that time, as we experience it, may be nothing more than a grand cosmic deception. Time feels inescapable. It permeates our lives, from alarm clocks jolting us awake to the relentless countdown to birthdays and deadlines. We measure our existence in seconds, minutes, and years, accepting this flow of time as an absolute, unyielding force. For centuries, this intuitive understanding of time was reinforced by the ideas of Sir Isaac Newton. He envisioned the universe as a vast stage with time serving as a universal clock, ticking away at the same steady rate for everyone and everything. But then came Albert Einstein, and our understanding of time was forever shattered. Einstein's theory of relativity revealed that time isn't a rigid constant, but a flexible participant in the cosmic dance. It bends, stretches, and warps depending on how fast you're moving and the strength of gravity's embrace. Imagine two identical clocks, one placed on Earth, the other aboard a spaceship hurtling near the speed of light. Bizarrely, if you could compare them, the clock on the spaceship would be ticking slower than the one on Earth. This mind-bending concept is time dilation. The faster you travel through space, the slower you travel through time. This isn't some abstract theory. It has real consequences. Imagine twins separated at birth. One stays on Earth, the other becomes an astronaut who spends years traveling at immense speeds. Upon their reunion, the spacefaring twin would have aged less than their Earth-bound sibling. Time would have literally passed slower for them due to the effects of time dilation. Time dilation may seem like science fiction, but it's a fact of our universe that engineers have to account for. GPS satellites, orbiting high above Earth and traveling at significant speeds, experience time slightly slower than we do on the ground. Their onboard clocks have to be adjusted to stay in sync, ensuring the maps on your phone remain accurate. Einstein's revolutionary theories upended our understanding of time. Suddenly, time wasn't a steady constant, but a dynamic player in the cosmic drama. This scientific upheaval sparked a resurgence in philosophical debates about the very nature of time. If time dilation and warped space-time are real, how do we reconcile these concepts with our everyday experience of time's constant flow? Let's explore some of the profound questions that emerge at the intersection of physics and philosophy. One central debate centers on the existence of the past and future. Presentists argue that only the present moment has any real existence. The past is a collection of memories, the future a realm of possibilities. Eternalists take the opposite stance, viewing all of the time, past, present, and future, as equally real and unchanging, like a vast unfurling tapestry. The growing block universe model attempts to bridge these two views. It posits a fixed past, an open future constantly branching into possibilities, and a continuously expanding present moment as our experience unfolds. These seemingly abstract philosophical debates have profound implications. If only the present exists, how can we learn from the past or plan for the future? If the future is already set, does that negate free will? The way we conceptualize time shapes how we understand our place in the universe and the choices we make within it. Perhaps the most unsettling implication of the block universe is the challenge it poses to free will. If the future already exists, laid out like a vast network of paths, are our choices truly our own? Or are we merely tracing a predetermined route? Our sense of agency nothing more than an illusion? This paradox forces us to grapple with the question of what it means to have control over our destiny within a universe where all moments may already be written. Can the block universe coexist with genuine free will? Some philosophers argue that even if our actions are fixed within a timeless expanse, we still experience the act of choosing and the consequences of those choices. Others suggest that true freedom might lie in accepting the predetermined nature of existence and finding meaning within that framework. Why does time seem to relentlessly march forward, never backward? Physicists and philosophers grapple with different arrows of time, each offering clues to the irreversible nature of events. The thermodynamic arrow is one of the most well-known. It stems from the second law of thermodynamics, which states that entropy, a measure of disorder, always increases in a closed system. This explains why eggs break but never unbreak, and why ice melts but doesn't spontaneously refreeze. These irreversible processes give us our sense of time moving in one direction. But thermodynamics isn't the whole story. Our minds create a powerful psychological arrow of time. We vividly remember the past, yet the future remains a mystery. Even the universe itself provides a cosmological arrow, as it continues to expand outward since the Big Bang. These diverse arrows raise a perplexing question. Is the flow of time a fundamental property of the universe, or a byproduct of how we experience the relentless unfolding of change? The bizarre realm of quantum mechanics throws a wrench into our traditional understanding of time and space. Consider the phenomena of entanglement, where two particles become linked in a profound way. Imagine a pair of gloves, one for your left hand, the other for your right. If those gloves are separated and placed in boxes on opposite sides of the planet, they remain intrinsically connected. If you open one box and find a right-handed glove, you instantaneously know, faster than any signal could travel, that the other box contains the left-handed glove. In the quantum realm, particles can become similarly entangled, their properties inextricably linked. Measuring one instantly affects the other, even across vast distances, seemingly faster than the speed of light allows. This paradox hints at a universe where connections might exist outside our usual understanding of linear time. Theories like loop quantum gravity go even further, suggesting space-time itself isn't a smooth continuum, but made up of tiny, indivisible chunks like the threads of a cosmic tapestry. If true, time might not be a fundamental force, but rather an emergent property of this deeper structure, a byproduct of the way these fundamental building blocks interact. These mind-bending theories force us to question the very nature of reality. Could it be that our experience of time's relentless flow is an illusion, born from our limited perspective within a universe that may operate on principles beyond our current comprehension? Perhaps the past, present, and future we perceive are merely convenient ways for our minds to organize the chaotic dance of existence. The true nature of time remains one of the universe's greatest enigmas. Is it a fundamental force woven into the fabric of existence, guiding the destinies of planets and particles alike? Or is it a grand illusion? A convenient fiction created by our own limited perspective? Scientific discoveries and philosophical paradoxes hint at the possibility that our experience of time's flow may be profoundly different from the true reality of the cosmos. If time doesn't exist as we perceive it, what does that mean for free will and our place within the grand story of the universe? Are the past, present, and future simply emergent constructs in a reality governed by laws beyond our current grasp? We may never possess the definitive answers to these questions, but the very act of pondering them reveals the profound beauty and endless mystery of existence. While the relentless march of the clock and the turning of the calendar may shape our daily lives, perhaps true freedom lies in embracing the timeless wonder of a universe that continually defies our understanding. There are countless untold stories in the universe, but one mystery veiled in the shadows of distant suns stands out prominently among many others. This discovery invites us to look beyond earthly boundaries and ponder untold possibilities. This is the story of Kepler 22b, a planet that's not just wandering in the void, but basking in the sweet spot, its star's habitable zone. Here, in this delicate balance, all conditions exist to ignite the magic of life, for the water to flow freely and the atmosphere to hold the secrets of existence. Discovered by the gaze of the Kepler Space Telescope, Kepler 22b invites us to ponder what worlds may lie beyond our own, to question our understanding of life and our role in the universe. It makes us dream of new horizons, of distant shores where humanity may one day set foot. Today we'll embark on a journey of discovery to unravel the mysteries of Kepler 22b and the countless other worlds that await us beyond our reach in the limitless expanse of space. In its search for Earth analogs scattered throughout the galaxy, the Kepler Space Telescope has become a pioneer, a celestial cartographer mapping the unknown. Initially, Kepler's mission was very clear: to observe the vastness of the Milky Way, looking for the faint twinkle of stars dimmed by the passing of planets in their orbit. Equipped with the most sensitive photometers, the telescope patiently watched the light of more than 150,000 stars. Among them, a pattern emerged: the rhythmic fadings of a particular star, not unlike our Sun. This was the first hint of Kepler 22b, a planet moving carefully around its star and briefly eclipsing its light, as if playing cosmic hide-and-seek. This discovery was a real event. The analytical skill required to sift through huge datasets and pick out planetary transits from the cacophony of cosmic noise was immense. It was akin to detecting a faint brightness difference caused by a moth flying in front of a lighthouse beam from thousands of miles away. The method of transits, Kepler's main tool, is a deceptively simple but very powerful technique. This method is based on the subtle interactions of planets orbiting their stars, passing in front of them for a moment and casting a small shadow, which then causes a slight dimming of the star's light. It's this faint, fleeting shadow that astronomers look for, a sure sign of a distant world orbiting its star. The elegance of the transit method lies in its simplicity and the wealth of information it provides. When a planet passes in front of its star, it blocks some of the starlight, causing a measurable dip in brightness. This dip, detected by instruments such as the Kepler photometer, is carefully analyzed to reveal not only the presence of the planet, but also its size. The amount of obscured light tells us how large a planet is compared to its star. Moreover, the regularity of these brightness variations reveals the planet's orbital period, the time it takes to complete one orbit around its star. This rhythm of disappearance and reappearance allows scientists to calculate how far away a planet is from its star, which provides crucial information about the planet's environment and its probability of habitation. This method also opens a window into the planet's atmosphere. When a star's light passes through a planet's atmosphere during transit, certain wavelengths of light are absorbed by atmospheric gases. By studying these changes in the star's spectrum, astronomers can determine the chemical composition of the planet's atmosphere, finding fingerprints of molecules that may indicate the presence of water, oxygen, or even signs of biological activity. The discovery of Kepler 22b was a watershed moment in the search for Earth analogs. It highlighted the incredible potential of our technology and the perseverance of scientists. This discovery has moved us further along the path of space exploration, opening new chapters in the history of the search for worlds that could one day become a second home for humanity. In the variety of cosmic interactions between planets and stars, there is a delicate region, a narrow band where conditions are just perfect. where the hope of life as we know it lingers in the darkness. This region, known as the habitable zone, is a cradle for potential life. A haven where water can exist in a liquid state, neither boiling under the fierce light of a star, nor freezing in the cold expanse of space. Imagine a world very similar to our Earth, located inside this life-supporting belt. Here, the heat from the star is neither too intense nor too weak, bathing the planet in soft light. And this is where Kepler-22b is, orbiting serenely in the habitable zone of its star, a prime candidate in the search for Earth-like conditions, and possibly life beyond our solar system. Just as Earth thrives in the Sun's habitable zone, Kepler-22b enjoys a similar privilege, orbiting at a distance where temperatures can allow lakes, rivers, and oceans to exist. The presence of liquid water, the universal solvent of many chemicals, is crucial, for it is in water that the chemistry of life unfolds. Water is the stage on which the drama of life is played out, from the simplest bacteria to the most complex forms of flora and fauna. Yet only the presence of water in a liquid state is one of the many conditions necessary to sustain life. What have we learned from analyzing this distant world? And is it so open to the theoretical presence of humans on it? As we dive into the mysteries of Kepler-22b, we embark on a journey of discovery, piecing together the puzzle of this distant world through the lens of our own Earth. With each observation, scientists are getting closer to understanding the fundamental nature of this distant planet, its size, its composition, and the very air that surrounds it. It's these factors that will help shed light on the presence of the basic components that may make this distant world a cradle for life. So, what are these factors? At the forefront of the search for life is, of course, the presence of liquid water, the cornerstone for all known biological processes on Earth. As we already know, Kepler-22b, which occupies a privileged position in the habitable zone, receives from its star a flow of energy that suggests that the temperature may be favorable for maintaining water in a liquid state. While the presence of liquid water is a promising start, the composition and behavior of Kepler-22b's atmosphere remains crucially unknown. Enveloping the planet, the atmosphere is the most important determinant of environmental conditions affecting temperature and surface pressure. Because the planet is in the habitable zone of its star, the theoretical presence of an atmosphere similar in composition to Earth's, rich in nitrogen and containing the requisite amount of oxygen and trace gases, could mean a temperate climate and stable water cycles similar to those that have nourished life on our home planet for billions of years. However, the range of possible atmospheric scenarios is enormous and shrouded in uncertainty due to our current technological limitations in directly observing exoplanet atmospheres at such great distances. If Kepler-22b's atmosphere tends toward a denser, carbon dioxide-dominated composition like that of Venus, this could lead to a greenhouse effect. In such a scenario, any potential water would exist as supercritical vapor at extreme pressures and temperatures. Conversely, an atmosphere that's too thin and free of greenhouse gases could turn Kepler-22b into a frigid world where water exists only as ice and the surface is exposed to harmful cosmic radiation. The equilibrium temperature of the planet, estimated at a comfortable 72 degrees Fahrenheit under Earth-like atmospheric conditions, indicates the possibility of an environment with ideal conditions for Earth-like life. However, if one were to go to the other extreme and create a Venus-like greenhouse effect, the surface temperature could soar to a scorching 860 degrees Fahrenheit, which would likely preclude the existence of life as we know it. Things get even more complicated. The elemental recipe for life goes beyond just water and the right atmosphere. Life, as we know it, is intricately woven from a variety of chemical elements, with carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur playing major roles. Sun-like stars, including Kepler-22, are G-type stars and typically have similar proportions of hydrogen and helium, with a small amount of heavier elements playing a primary role. However, during planetary system formation, the distribution and concentration of materials in the protoplanetary disk around the nascent star influence the further composition of the forming planets. Temperature gradients in this disk lead to condensation of different materials at different distances from the star, which affects the composition of the planets. Once a planet is formed, its composition can be altered by differentiation, the separation of different materials within the planet, resulting in the formation of distinct layers, such as the core, mantle, and crust, and geologic processes such as volcanic activity and plate tectonics. So while direct measurements of the chemical composition of Kepler-22b are beyond our capabilities, the diversity of elements in the universe and the planet's location in a habitable zone can only hint at the exciting possibility of the presence of the building blocks that create the basis for the complex chemistry of life. While we wonder whether the planet's atmosphere might contain a protective layer like ours, or whether it's a dense, oppressive cloak trapping heat as a result of the greenhouse effect, and what the planet's chemical composition actually is, one thing we know for sure: the last, fourth parameter necessary for life is in almost perfect agreement. The complexity of life must necessarily be fueled by energy, and the presence of Kepler-22b in the habitable zone ensures its constant supply from the host star. This energy, which powers photosynthesis on Earth, could drive the fundamental biological processes necessary for life on this distant planet. The characteristics of a star that is slightly cooler and smaller than our Sun, but similar in many ways, provides a stable source of light and heat. Against the grand landscape of the cosmos, Kepler-22b stands out as a beacon of possibility, a world where the basic ingredients for life as we know it can come together. Yet the true nature of this distant planet remains shrouded in mystery, reminding us of the vast unknowns that await us as we continue to search for the secrets of the universe and the potential for life beyond our solar system. The search for signs of extraterrestrial life is the cornerstone of our celestial explorations, compelling us to venture into the unknown with hope and scientific rigor. As we turn our eyes toward distant worlds like Kepler-22b, the next generation of telescopes and space missions are poised to pierce the cosmic veil, inviting us to peer into the atmospheres of these distant planets and learn their secrets. At the forefront of this cosmic quest is the James Webb Space Telescope, the most sophisticated and powerful space telescope ever built. With unprecedented resolution and sensitivity, the JWST is designed to observe the universe in the infrared, enabling it to detect the faint reflections of light from the earliest stars and galaxies and, crucially, the atmospheric signatures of exoplanets. The JWST suite of instruments carefully analyzes light passing through the atmosphere of exoplanets as they transit their host stars. This process, known as transmission spectroscopy, will allow scientists to decipher the composition of the atmospheres of these worlds in search of characteristic signatures of molecules essential for life, such as water vapor, oxygen, and methane. The mission of the Transiting Exoplanet Survey Satellite, or TESS, launched in 2018 and complementing JWST, is to survey the brightest stars near Earth for transiting exoplanets. Building on the legacy of the Kepler mission, TESS is casting a wider net, revealing many new worlds for further study. Among them, planets that share characteristics with Kepler-22b will be prime targets for detailed atmospheric analysis, opening up new opportunities to search for biosignatures. Coming down to Earth, the Extremely Large Telescope, or ELT, which, when completed, will be the world's largest optical telescope, will be another powerful tool in the search for alien life. The ELT's colossal mirror located atop Cerro Armazones in Chile's Atacama Desert. We'll collect light from distant exoplanets, allowing direct images and spectroscopic studies of their atmospheres. Its advanced instruments will be able to detect even the faintest chemical fingerprints, further expanding our understanding of such distant worlds. Looking ahead, proposed missions such as the Habitable Exoplanet Observatory, HABEX, and the Large UV Optical IR Surveyor, LUVOIR, promise to push the boundaries of exoplanet research even further. Equipped with advanced technology such as coronagraphs and star shades, these observatories aim to directly image exoplanets by dissecting their light to reveal the molecular composition of their atmospheres in unprecedented detail. The hunt for alien life embodied in exploring such planets continues to inspire and stimulate the human spirit, reminding us that the search for life beyond Earth is more than just a scientific endeavor. It's a profound exploration of our place in the cosmos. As we stand on the threshold of discovery, our thoughts drift to the distant world of Kepler-22b, a planet in the nourishing embrace of its star's habitable zone. Here, in this hypothetical realm, we imagine the possibilities such a world might hold. Could it be that the hilly landscapes of this distant planet are home to a diversity of alien flora thriving in the soft light of Kepler-22? Could it also be that its seas are teeming with life, with forms both strange and outlandish, adapted to the unique conditions of this distant world? And what is humanity's potential role in such a world? For now, it's hard to imagine, but these dreams are underpinned by the relentless pursuit of knowledge that defines our current path in exoplanet exploration. As we gaze into the heavens with instruments such as the James Webb Space Telescope, the Transiting Exoplanet Survey Satellite, and the upcoming the Extremely Large Telescope, we continue to push the boundaries of our understanding. Each discovery adds its own piece to the great puzzle of the cosmos, revealing the diversity of worlds that inhabit our galactic neighborhood. The future of exoplanet exploration promises to deepen our understanding and knowledge of distant worlds and redefine our place in the universe. As we stand at this crossroads of imagination and discovery, we remind ourselves that the search for life beyond Earth and the understanding of humanity's future potential among the stars is a reflection of our deepest desires to explore, understand, and reconnect with the vast, wondrous cosmos that is our home. In a universe dominated by ancient, massive structures, there are places where something unexpected happens that defies the cosmic norm. New galaxies emerge. These rare formations are changing our idea of how the cosmos should behave. While the Milky Way and Andromeda seem to have entered their mature phase, somewhere out there in the far corners of space, young galaxies are still being born, glowing with the energy of new star formation. But why do these exceptions exist? What forces allow them to thrive when the rest of the universe has slowed down? By exploring these distant regions, we learn about the forces that lead to the formation of such grand structures, the role of dark matter in all of this, and the mysterious processes that allow some galaxies to defy the passage of time. The discovery and classification of galaxies was a milestone in our understanding of the universe. In the early 20th century, observations by Edwin Hubble showed that the nebulae observed in telescopes were not just gas clouds inside our galaxy, but entire galaxies, each containing billions of stars. This discovery expanded our understanding of the cosmos beyond the Milky Way, revealing a universe teeming with distant galaxies. Soon, galaxies were categorized by their shape: spiral, elliptical, and irregular. These classifications helped astronomers create a more organized view of the cosmos, which led to further study of the origin and evolution of these huge structures. However, as our observations deepened, a surprising pattern emerged. The vast majority of galaxies observed were ancient, dating back almost to the very beginning of the universe. This discovery was unexpected. When the first detailed studies of galaxies were conducted, scientists expected to find a range of galaxy ages, including recently formed galaxies. However, instead of a universe full of young galaxies still in the formation stage, they found that most galaxies had already reached maturity. These findings challenged existing theories of cosmic evolution at the time, raising questions about how and when galaxies formed. At first, the scientific community was stunned. The rarity of young galaxies seemed to contradict the ongoing process of star formation that's still observed in the universe today. This paradox, the presence of ongoing star formation in predominantly ancient galaxies, posed a serious question to our understanding of galaxy formation and evolution. As astronomers delved deeper into this mystery, they began to realize that the formation of galaxies may not be as simple as previously thought. The processes that govern the early universe, such as the distribution of dark matter and the influence of cosmic structures, seem to have played a more important role in shaping its landscape than first thought. These factors likely contributed to the rapid formation of galaxies shortly after the Big Bang, leading to a shortage of newly formed ones in the modern era. Determining the age of galaxies is a complex task that relies on a variety of methods, most of which focus on the age of the stars within them. For example, astronomers have used several methods to estimate the age of the stellar population of the Milky Way and Andromeda. One of the main methods involves studying the distribution of stars in the Hertzsprung-Russell diagram, or HR diagram, which shows the dependence of the luminosity of stars on their temperature. In particular, astronomers focus on the turning point of the main sequence, the stage at which stars begin to leave the main sequence and turn into red giants. This point is very sensitive to age. The position of the pivot point on the HR diagram can give an accurate estimate of the age of the stellar population. Another important method is the study of globular clusters, dense groups of ancient stars orbiting around the outskirts of galaxies. The age of these clusters is also determined by the rotation points of the main sequence of their stars. And since globular clusters are among the oldest objects in the galaxy, they provide crucial clues about their formation history. For example, the oldest globular clusters in the Milky Way are about 13 billion years old, indicating that the Milky Way itself formed shortly after the Big Bang. In addition to studying star clusters, astronomers also use spectral analysis. By analyzing light spectra, particularly absorption lines, they can determine the relative proportions of different types of stars. Older galaxies are dominated by red, cooler stars, while younger galaxies have more blue, hotter stars. The discovery that many galaxies, including the Milky Way, formed nearly 13.8 billion years ago, shortly after the Big Bang, was a significant breakthrough in cosmology. The rapid collapse of clouds of primordial gas under the influence of dark matter probably played a crucial role in these early formations. This process laid the foundation for the cosmic structures we see today. So the formation of galaxies in the early universe is a story deeply intertwined with the mysterious and influential presence of dark matter. In the chaotic period after the Big Bang, the universe was a hot, dense soup of particles in which matter and radiation were tightly bound together. As the universe expanded and cooled, gravity began to pull matter together into the first structures, tiny clumps of matter known as proto-galaxies. According to scientists, dark matter played a key role in this process. Unlike ordinary matter, which interacts through the electromagnetic forces and radiation, dark matter interacts mainly through gravity. Because of this, dark matter began to stick together earlier than ordinary matter, forming the basis on which the first galaxies eventually formed. These dense regions of dark matter, often called dark matter halos, provided the gravitational wells needed to pull in gas and dust, leading to the formation of the first stars and eventually the first galaxies. These early galaxies were relatively small and simple compared to the huge and complex galaxies we see today. They were often irregularly shaped and lacking a distinct structure, such as that of the Milky Way. But over time, driven by the gravitational pull of dark matter, these proto-galaxies began to merge and interact. As proto-galaxies merged, they grew in size and complexity, forming more massive structures that eventually evolved into the spirals, ellipticals, and irregular shapes that populate the modern universe. This period of intense formation and merger is often referred to as cosmic noon, a time of active star formation and growth through mergers at a much higher rate than we observe in the modern universe. So why are newly formed galaxies such a rarity in the modern universe? One of the key factors contributing to this phenomenon was the very process of galaxy mergers. In the early universe, when galaxies were smaller and more numerous, there were frequent interactions and collisions between them. However, as the universe expanded and matured, such collisions became less frequent, resulting in fewer new galaxies. Another factor is the changing influence of dark matter halos. In the early universe, halos were smaller and more concentrated, favoring the collapse of gas and the formation of new stars and galaxies. As the universe expanded, it became larger and more diffuse, making it harder for the gas to cool and condense into new formations. The large-scale structure of the universe, often referred to as the cosmic web, also plays a notable role in this process. Galaxies are not randomly distributed, but are arranged along huge threads of dark matter that stretch across the cosmos, connecting galaxy clusters. Along these threads, gas flows into them, fueling the star formation process. However, in the present epoch, most of the gas has already been consumed or trapped in larger and more stable structures, which also leads to a decrease in the rate of new formation. However, despite all that we've just said, there are rare cases that violate this trend. One such example is the dwarf irregular galaxy known as Zwicky 18. Located about 45 million light-years away, this galaxy is notable for having a relatively recent burst of star formation. Unlike most, Zwicky 18 began its first major burst of star formation only about 500 million years ago, well after the period when most galaxies in the universe were fully formed. The slow evolution of Zwicky 18 represents an intriguing case in the study of galaxy formation. Its star-forming regions are characterized by intense ultraviolet emission and stellar winds from young massive stars. The presence of these young stars, combined with the overall low metallicity, suggests that Zwicky 18 did not undergo the same evolutionary processes as most other galaxies. This late bloom may provide clues to the conditions favoring delayed star formation and raise the question of the role of environmental factors, such as nearby galaxy interactions in triggering or suppressing star formation. Another notable case is a galaxy with a rather unwieldy name of HSC J1631 plus 4426, discovered through observations with a Subaru telescope. Located 430 million light-years away, this specimen is not only young, but also holds the record for the lowest observed oxygen content. The low oxygen content indicates that the galaxy is in the very early stages of its formation and has only recently begun to convert primordial hydrogen and helium into heavier elements through stellar nucleosynthesis. The galaxy's small size, about 0.8 million solar masses, comparable to a star cluster in our Milky Way, further emphasizes its youth. The fact that such a young and small specimen exists so late in the history of the universe is surprising, given that in the early universe, the conditions for galaxy formation were much more favorable. And given that the expansion of the universe continues to accelerate, making conditions for the formation of new galaxies more and more impossible, such findings become quite extraordinary. At the same time, star formation is a continuous process that continues even in ancient galaxies. And star clusters such as the Pleiades provide clear evidence of this ongoing activity. The Pleiades, often referred to as the Seven Sisters, is a young open star cluster located just 448 light-years from Earth. Despite the age of the Milky Way galaxy being over 13 billion years old, the Pleiades cluster is a relative newcomer, having formed only about 100 million years ago. This indicates that even in such a mature galaxy as ours, there are still regions of active star formation. The formation of star clusters like the Pleiades usually occurs in regions of galaxies where there's a high concentration of gas and dust. These molecular clouds collapse under their gravity, giving birth to new stars. In the case of the Pleiades, the stars of the cluster are still relatively young and hot, and they emit bright blue light, making the cluster visible to the naked eye. Such star clusters are not unique to our galaxy. In neighboring galaxies, such as the Large Magellanic Cloud, abbreviated LMC, star formation is also ongoing. The LMC, a companion galaxy to the Milky Way, contains the oldest known stars as well as regions where new ones are still forming. One such ancient star, LMC 119, that was only discovered this year, is believed by scientists to be about 13 billion years old. This discovery highlights the remarkable longevity of some stars and suggests the conditions for star formation are still not fully understood by us. These star-forming regions are not just remnants of the past, but a critical factor in the future evolution of galaxies. As new stars form, they contribute to ongoing dynamical processes in their host galaxies, affecting everything from the formation of planetary systems to the distribution of elements necessary for life. While star formation continues in some regions of galaxies, like the Milky Way, a significant factor affecting the overall evolution of these galaxies is the presence of the previously mentioned dark matter halos. These halos extend far beyond the visible edges of galaxies and play a crucial role in their formation and structure. As we know, dark matter has a significant gravitational influence on galaxies. This influence is most evident in the way galaxies rotate. Observations have shown that the outer regions of spiral galaxies, including the Milky Way, rotate much faster than would be expected with only visible matter. This discrepancy suggests the presence of a massive invisible component forming a spherical halo around the galaxy. The dark matter halo not only stabilizes galaxies, but also affects their ability to form new stars, and, consequently, new galaxies. In the early universe, dark matter halos provided the gravitational wells necessary for the collapse of gas and the formation of the first galaxies. Over time, however, these halos grew in size and became more diffuse, preventing the formation of new galaxies. The expanding halos, with their enormous gravitational influence, can prevent the gas from cooling and condensing into new stars, effectively suppressing the birth of new galaxies in the current epoch. These dynamics create a delicate balance in the cosmos, where dark matter both promotes and inhibits the growth of cosmic structures. According to scientists, the presence of such halos is one of the key reasons why we see fewer new galaxies forming today compared to the early universe, marking a significant shift in cosmic evolution. Understanding the formation and evolution of galaxies remains one of the most serious challenges of cosmology. Despite significant progress, debates about the fundamental processes that shape the universe are still ongoing. one of the key debates concerns the formation of structures in the cosmos, whether it occurs according to the top-down or bottom-up approach. According to the top-down model, large cosmic structures form first, and then they break up into smaller galaxies and clusters. According to this model, the largest galaxies and galaxy clusters appeared at the very beginning of the universe's history, and smaller structures were formed as these large structures decayed. In contrast, the bottom-up model suggests that small structures formed first, and tiny proto-galaxies and star clusters eventually merged to form larger galaxies and clusters. This theory is consistent with the observed hierarchical nature of the universe, where small objects merge into more complex and massive systems over billions of years. Although these models provide a foundation for understanding galaxy formation, recent observations have revealed complexities that challenge both theories. For example, the discovery of ancient massive galaxies in the early universe suggests a more subtle interaction between these processes, perhaps indicating that the true nature of cosmic evolution is a combination of both scenarios. Nevertheless, the search for and understanding of new galaxies continues to drive astronomical research. JWST has already opened new windows into the distant universe, allowing astronomers to peer into an era when galaxies were just forming. One of the most intriguing questions is whether new galaxies are still forming today. While the early universe was fertile ground for galaxies to form, today's cosmic landscape presents a different picture. As the universe expands and dark energy accelerates this expansion, conditions suitable for galaxy formation become increasingly rare. Future astronomical missions are poised to push the boundaries of our knowledge even further. Instruments such as the Vera C. Rubin Observatory and the European Space Agency's Euclid mission will shortly carry out deep space surveys that are likely to reveal new galaxies that have eluded previous observations. These missions are aimed not only at discovering new galaxies, but also at unlocking the mysteries of dark matter, dark energy, and the overarching structure of the universe. History of the universe is far from complete. As we continue to explore the cosmos, discoveries change our understanding and raise new questions. Each glimpse into the distant past brings us closer to unraveling the mysteries of the universe's formation and fate. Stay tuned for more discoveries to come. In the vast, silent expanse of our solar system, beyond the familiar brilliance of Neptune, rumors of some unseen presence have been stirring astronomers for quite a few years now. This mysterious force, unseen but undeniable, stretches the very fabric of our cosmic neighborhood, bending the paths of distant objects with its invisible grip. Here in the shadowy depths of space, where the warmth of the sun barely reaches, lies a mystery that's baffled the brightest minds. The hypothetical world known only as Planet 9, whose existence can be determined not by direct observation, but only by the subtle interaction of trans-Neptunian objects performing complex orbital motion. Could there be a rogue planet shrouded in the darkness of space, exerting its influence from afar? A world that defies our understanding and challenges the very limits of what we know about our solar system. Join us as we piece together clues scattered in the back of the solar system in search of a planet that has so far eluded our sight. In the early 1990s, the outer reaches of our solar system began to reveal their secrets. Astronomers discovered a region teeming with icy bodies, now known as the Kuiper Belt. This discovery marked the beginning of a new chapter in our cosmic journey, expanding our understanding of the boundaries of the solar system. Among these distant wanderers was Pluto, long considered the ninth planet and proudly bearing that title since its discovery in 1930. But as the Kuiper Belt uncovered its treasures, Pluto's status began to be questioned. The discovery of objects such as Eris that rivaled and even surpassed Pluto in size sparked a debate that shook the foundations of planetary classification. In 2006, the International Astronomical Union was faced with an unresolved situation. What defines a planet? The answer to this question led to a controversial decision that downgraded Pluto to a dwarf planet. This decision, met with both approval and opposition, has swept through the astronomical community and the public, redefining the way we think about the solar system. In this cosmic controversy, however, the seeds of a new mystery were sown: the peculiar orbits of some Kuiper belt objects, including the then distant newly discovered Sedna, hinted at an invisible influence from the shadows guiding these icy bodies. Could it be that another planet, hidden in the vastness of space, created the architecture of the outer solar system? This question ignited the imagination of astronomers like Mike Brown and Konstantin Batygin, who set out to find the truth. Their journey will lead them to speculate on the existence of Planet 9, a hypothetical world hiding behind Neptune, whose presence is signaled only by the interaction of the most distant members of the Kuiper belt. A new planet emerging from the heart of controversy awaits discovery. As we move beyond the familiar boundaries of the inner solar system, a realm of icy bodies and distant orbits opens up before us. Here, in the cold, dark regions beyond Neptune, lies an enigma that has captivated astronomers for years. It's the Kuiper belt, a vast ring of debris left over from the formation of the solar system. Among these celestial wanderers, a separate group shows peculiar behavior that contradicts the expected norms of orbital mechanics. These are detached TNOs, or trans-Neptunian objects, whose paths are free of Neptune's gravitational influence, and extreme trans-Neptunian objects, or ETNOs, whose orbits are so eccentric that they seem to be tethered to some invisible force. What could be the architect of this unusual behavior? The answer may lie in the gravitational anomalies that pervade this distant region. These anomalies, subtle but deep, indicate the presence of a massive object whose gravitational pull shapes the orbits of these distant objects. The detached TNOs, whose orbits seem to be unaffected by Neptune, hint at a disturbance in the gravitational harmony of the outer solar system. Meanwhile, ETNOs, with their extreme orbits, paint a picture of cosmic interaction guided by a hidden force. The quest to understand these gravitational mysteries led researchers to hypothesize the existence of Planet 9, a hypothetical world whose mass and orbit could explain these anomalies. By carefully mapping the orbits of these mysterious objects, scientists began piecing together the potential location and characteristics of this invisible planet. In the tranquil balance of our solar system, each planet plays its part, revolving around the sun in a centuries and centuries and centuries old rhythm. But beyond this familiar rhythm looms a shadowy figure, a silent participant whose presence is felt but not seen. Let's take a closer look at the Planet 9 hypothesis itself. In 2014, astronomers Chad Trujillo and Scott S. Shepard noted an intriguing similarity between the orbits of Sedna, 2012 VP113, and several other ETNOs, a phenomenon too unusual to be a mere coincidence. Trujillo and Shepard made a bold suggestion: the existence of an unknown planet whose orbit is a perfect circle between 200 and 300 astronomical units from the Sun. A few years later, in 2016, Mike Brown and Konstantin Batygin embarked on an intellectual journey delving into the mysteries of the outer solar system in order to develop this hypothesis. Through careful analysis and computational modeling, Brown and Batygin pieced together previously found gravitational anomalies that indicated the existence of a massive invisible planet. This hypothetical world, in their opinion, could be the key to unraveling the special dynamics of the outer part of the solar system. As their research progressed, so did their understanding of the potential characteristics of Planet 9. Its mass was originally thought to be 10 times that of Earth, but further research revealed that its mass was slightly less, but still significant, at about 5 or 6 Earth masses. This revision painted a picture of a planet powerful enough to control the orbits of distant objects, yet elusive enough to remain hidden from our most powerful telescopes. The influence of this hypothetical planet extends far beyond its immediate vicinity. Its gravitational influence can explain the clustering of the orbits of detached TNOs and the extreme trajectories of ETNOs, weaving together a complex picture of celestial mechanics. The hypothesis of Planet 9 sparked a flurry of scientific research, and astronomers around the world joined the hunt for this elusive neighbor. The search for Planet 9 is a journey fraught with difficulty, a testament to both the vastness of the universe and the limitations of our current technological capabilities. Its distant orbit, presumably huge and elliptical, leads it through the farthest reaches of our system. This region, where the light of the sun is almost unattainable, envelops the planet in total darkness. This remoteness poses a serious problem because the potential position of the planet can encompass vast portions of the sky, requiring extensive, focused searches covering these celestial expanses in painstaking detail. It's something akin to trying to find a needle in an astronomical haystack. Moreover, because of its distance from the sun, the planet's surface temperature is extremely low, meaning it emits minimal thermal radiation, making infrared detection just as difficult. The lack of emitted and reflected light is compounded by the glare of distant stars and the myriad cosmic objects that fill the sky, each vying for the attention of our telescopes. Among other difficulties, the nature of the search is compounded by the planet's enormous orbital period, which is thought to be thousands of years. Because the planet's motion across the sky is imperceptibly slow from our earthly perspective. Even after a decade, Planet 9's position in space will have changed only slightly, making any attempt to observe its motion in the short term virtually impossible. This chilling rate of motion means that traditional methods of detecting planets by observing their transit or motion against the background of stars are not feasible. However, in their relentless pursuit, astronomers use an array of sophisticated techniques and instruments, from ground-based telescopes equipped with advanced adaptive optics to space-based observatories that circumvent the Earth's atmospheric distortions. So, in the pursuit of Planet 9, astronomers have had to go beyond traditional observational methods, leading to the development of several innovative approaches aimed at refining the elusive planet's location. They utilize unique aspects of the solar system's external environment and potential celestial interactions that Planet 9 may have with other objects. One of the proposed approaches has to do with potential moons that may orbit around Planet 9. Given its considerable mass, it is conceivable that it could have captured one or more moons during its long journey through the solar system. The concept is based on the process of tidal heating, a phenomenon in which the gravitational interaction between a planet and its moon causes internal heat to be released within the moon, potentially making it warmer than the parent planet. This is what allows the satellites Europa and Enceladus to have liquid subsurface oceans and also provokes vigorous volcanic activity on Io. This internal heating may cause the moons to emit infrared radiation more perceptively than Planet 9 itself, providing an indirect but promising avenue for detection. Another innovative method involves tracking the trajectories of interstellar asteroids passing through our solar system. These high-speed objects coming from regions outside our solar system could potentially be affected by the gravitational pull of Planet 9. By meticulously tracking the trajectories of such asteroids, astronomers can infer the presence and location of a planet from the subtle gravitational jolts it exerts on passing bodies. This method was demonstrated by studying the interstellar asteroid Oumuamua, whose path through our solar system may have been slightly altered by such a massive object. The trajectories of spacecraft passing through the outer solar system can also provide valuable insights. Like asteroids, when spacecraft travel vast distances between planets, their trajectories are slightly and subtly influenced by the gravitational forces they encounter. By analyzing the precise tracking data from these missions, scientists can detect unaccounted gravitational anomalies that may hint at the presence of Planet 9. This method requires accumulating huge amounts of data over long periods because the gravitational effects are incredibly subtle. However, the results can be very significant and will pay off the time spent. Moving from direct observation to indirect detection through a planet's influence on its environment may be the key to unlocking one of the greatest mysteries of our cosmic neighborhood. The search for Planet 9 has also spawned many theories and speculations about the true nature of this elusive object. Among the most intriguing are hypotheses that Planet 9 could be a primordial black hole or a dense dark matter clump, each representing a radical departure from the traditional planetary view. The idea that Planet 9 could be a primordial black hole introduces a sharp twist to the narrative. Unlike stellar black holes, formed by the collapse of massive stars, primordial black holes are theorized to have originated in a high-density environment shortly after the Big Bang. These hypothetical entities may be the size of an asteroid, but have the mass of a planet. The possibility that Planet 9 is one of these ancient, mysterious objects is compelling for several reasons. First, it would allow us to explain the gravitational effects attributed to it without the need for a visible planetary body. Secondly, this of course does not completely contradict the impossibility of its detection, since such an object would theoretically be no larger than a basketball. According to another theory, Planet 9 may be a concentrated blob of dark matter. This form of matter, which does not emit, absorb, or reflect light, accounts for a significant portion of the total mass of the universe, but remains one of the greatest mysteries. Dark matter clumps, theoretical clusters of dark matter, are thought to have arisen from density fluctuations in the early universe. As the universe expanded and cooled, these gravitational fluctuations led to the formation of dark matter structures ranging from small clumps to massive halos surrounding galaxies. If Planet 9 were a dense cluster of dark matter, it could exert the gravitational influence observed in the outer solar system without being directly observable using conventional telescopic techniques. The primordial black hole and dark matter clot hypotheses emphasize the profound implications of the search for Planet 9 far beyond the discovery of a new member of the solar system. Whether it's an ordinary planet, a primordial black hole, or a dark matter clot, one way or another we'll find ourselves on the favorable side of events. The search for Planet 9 is a testament to humanity's enduring curiosity and relentless pursuit of the unknown. A recent preprint of a research paper by the same Mike Brown and Konstantin Batygin and their colleague Matthew J. Holman entitled Pan-STARRS 1 Search for Planet 9, dated February 1, 2024, reflects the meticulous ongoing efforts to uncover this enigmatic member of our solar system. The study used extensive data from the Pan-STARRS 1 survey, which, with its deep and wide sky coverage, provided a unique vantage point for the search. By focusing on single-night transients and using a sophisticated Keplerian orbit linking algorithm, the researchers sifted through billions of detected objects, a task akin to finding a single grain of sand among the entire North American coastline. This methodological approach represents a significant leap forward, building on the foundation laid by previous surveys such as the Zwicky Transient Facility and the Dark Energy Survey. Despite the depth and breadth of the PS1 survey, the elusive ninth planet remained out of sight. No features matching the search parameters were found in the data. This result, while not leading to the discovery of a ninth planet, nevertheless narrowed the search area considerably, excluding 78% of the parameter space in which the planet could potentially reside. The remaining 22%, areas with poor observational coverage or inaccessible to current detection capabilities, represent the next frontier in this space search. The journey doesn't end with the PS1 research. The upcoming launch of the Vera C. Rubin Observatory promises to usher in a new era of astronomical observation with capabilities that can finally pierce the veil of mystery, including that which surrounds Planet 9. As we stand on the threshold of these future explorations, the search for Planet 9 remains a beacon of scientific inquiry, a reminder of the vastness of the universe and the small but significant place we occupy in it. What if the closest star to our Sun is hiding a world where humans might one day live? In 2016, astronomers discovered Proxima Centauri b, a planet just 4 light-years away. But getting to this distant neighbor isn't just a dream. It's a challenge that modern science is beginning to address. Imagine a journey of more than 25 trillion miles. The technology we have today, such as the ion engines used in deep space missions, pales in comparison to what would be needed for such a journey. But hidden in the blueprints of a decade ago and cutting-edge research are the keys to interstellar travel. But distance isn't the only obstacle we have to overcome. Today, we'll talk about it and find out if humanity's next giant leap can take us to Alpha Centauri. The dream of interstellar travel has been part of the human imagination for centuries. But it wasn't until the 20th century that science began to catch up with science fiction. The journey begins with a momentous moment in 1961, when Yuri Gagarin became the first man to orbit the Earth. This achievement paved the way for space exploration, proving that humans could survive and work beyond our planet. Then came the Apollo program, including the historic 1969 lunar landing. Neil Armstrong and Buzz Aldrin's footsteps on the lunar surface were not only victory for humanity, but also a demonstration of our ability to reach and explore other celestial bodies. In the 1970s, Voyager missions provided invaluable data on the outer planets and heliosphere. These probes, now in interstellar space, carry with them golden records, messages intended for any intelligent extraterrestrial life that might encounter them. The voyages of Voyager 1 and Voyager 2 have given us a glimpse of the vastness of space and the inspiring potential of travel beyond our solar system. But humanity does not stand still. In recent years, the development of advanced propulsion systems has been crucial. Ion engines, used in missions such as NASA's Dawn spacecraft, enable long-duration missions with unprecedented efficiency. These engines use electrically charged particles to generate thrust, a method far more efficient than traditional chemical rockets. At the same time, our understanding of the universe has been revolutionized with the discovery of exoplanets, planets orbiting stars outside our solar system. The first confirmed exoplanet discovery occurred in 1992 when astronomers discovered 2 rocky planets orbiting a pulsar. This discovery shattered previous notions and opened the floodgates to the search for other worlds. In 1995, the discovery of 51 Pegasi b, the first exoplanet found orbiting a Sun-like star, further reinforced the idea that planets are fairly common in the universe. This gas giant, located about 50 light-years away, ushered in an era of exoplanet discoveries that continues to this day. Among the most exciting discoveries is Proxima Centauri b, discovered only in 2016. This exoplanet orbits Proxima Centauri, the closest star to our Sun, at a distance of only 4.24 light-years. Proxima Centauri b is in the habitable zone of its star, where all the conditions for liquid water to exist could exist. This proximity and potential habitability make this planet a prime target for future exploration and even potential colonization. The discovery of Proxima Centauri b was made possible thanks to the radial velocity method, which allows you to detect subtle fluctuations in the motion of the star caused by the gravitational pull of the orbiting planet. So far, this method has helped to identify more than 1,000 exoplanets. each of which has become the next step in the search for a world on which life may exist. The feasibility of interstellar travel depends directly on our ability to develop efficient and powerful propulsion systems. Current space travel technology has made significant advances, but it still falls short of what's needed to travel beyond our solar system. Ion engines represent one of the most advanced forms of space propulsion in use today. Unlike traditional chemical rockets, which use explosive reactions to create thrust, ion engines use electricity to ionize the propellant, usually xenon gas. The ionized gas is then accelerated using an electric field, creating sustained and highly efficient thrust. NASA's Dawn spacecraft, launched in 2007, is a prime example of the capabilities of ion propulsion. Dawn's mission was to explore the asteroid belt, in particular the protoplanet Vesta and the dwarf planet Ceres. Ion propulsion allowed Dawn to enter and exit orbits around these bodies, which would have been prohibitively expensive with conventional rockets. Ion engines have a high specific impulse, which means they use fuel much more efficiently than chemical rockets. This efficiency is critical for long-duration missions because it allows spacecraft to take less fuel with them. However, the trade-off is that ion engines produce much less thrust than chemical rockets. This makes them unsuitable for launching spacecraft from the Earth's surface, where enormous thrust is needed to overcome gravity. Another milestone in the development of modern propulsion technologies was NASA's New Horizons probe. Launched in 2006, the spacecraft was supposed to explore Pluto and its moons, providing mankind with the first images of this distant world from an incredibly close distance. The probe's journey did not stop at Pluto, but continued on to the Kuiper Belt, a region filled with icy bodies and remnants of the formation of the solar system. New Horizons used a combination of chemical propulsion and gravity assists to achieve its high speed. After launch, the spacecraft received gravitational assistance from Jupiter, which increased its speed and directed it toward Pluto. This maneuver allowed New Horizons to travel more than 3 billion miles in just 9 years. An amazing accomplishment considering such vast distances. While New Horizons demonstrates the height of current space travel capabilities, it also highlights its limitations. Despite speeds of more than 36,000 miles per hour, it took the spacecraft nearly a decade to reach Pluto, and even longer to continue its journey into the Kuiper Belt. For interstellar travel, where distances are measured in light years, we need propulsion systems capable of much higher speeds over long periods of time. Meanwhile, the most intriguing and historically significant advanced propulsion concept is nuclear pulse propulsion. This technology, conceived during the Cold War era, involves using a series of controlled nuclear explosions to propel a spacecraft. The concept was first proposed by physicist Stanislaw Ulam in the 1950s and later developed into the Orion project. The basic principle of nuclear pulse propulsion is relatively simple. Small nuclear bombs are thrown behind the spacecraft and detonated, and the resulting explosions provide powerful thrust. A large pusher plate attached to the spacecraft absorbs the force of the explosion, propelling the spacecraft forward. The potential of the Orion project was enormous. Calculations showed that such a spacecraft could reach speeds of up to 10% of the speed of light, making it one of the fastest of the proposed propulsion methods. Such a capability would significantly reduce travel time to nearby star systems, including our neighbor, Alpha Centauri. Meanwhile, in recent years, the Breakthrough Starshot initiative has become one of the most ambitious attempts to achieve interstellar travel within our lifetime. The goal of this international science project is to send a probe to the same Alpha Centauri and possibly reach it in just 20 years. breakthrough starshot's main innovation is the use of a light sail propelled by an array of powerful ground-based lasers. This light sail, which is a thin and highly reflective sheet, will accelerate to extremely high speeds by transmitting momentum from millions of laser beams. Unlike traditional propulsion methods, this system carries no fuel, making it extremely lightweight and, in theory, capable of speeds up to 20% of the speed of light. Realizing this technology, however, is not without its challenges. The proposed laser array would require a total optical power of about 100 gigawatts, about 100 times the capacity of the world's largest battery. Synchronizing the roughly 100 million lasers to focus their beams on the light sail is a daunting technical hurdle. To solve this problem, researchers from the Australian National University have proposed using a laser guide satellite to help maintain an accurate target throughout the voyage. Despite such challenges, the potential benefits of this technology are enormous. If successful, the Breakthrough Starshot mission will be able to transmit detailed scientific data and images from Alpha Centauri, providing unprecedented insight into our nearest neighboring star system. While light sails represent a promising near-future technology, other cutting-edge concepts are pushing the boundaries of our understanding of physics. Among them is the theoretical warp drive. Inspired by Einstein's general theory of relativity, a warp engine would manipulate space-time itself, compressing space in front of the spacecraft and expanding it behind, allowing the craft to travel faster than the speed of light without violating the laws of physics. The concept of warp drive gained attention after the 1994 publication of a paper by physicist Miguel Alcubierre, who proposed a theoretical basis for such a drive. Although the concept is currently speculative and requires exotic matter with negative energy density, warp drive remains a tantalizing possibility for future interstellar travel. Another innovative concept is the Freeman-Dyson interstellar jet engine. This hypothetical propulsion system would harness the energy of a star, using a series of mirrors or lenses to focus stellar energy onto a spacecraft. The collected energy would then be converted into thrust, propelling the spacecraft at high speeds. While Dyson's concept is intriguing, its practical realization faces serious obstacles. Capturing and converting enough stellar energy to achieve meaningful thrust would require materials and engineering capabilities many times greater than our current technology. Perhaps the most powerful of the proposed propulsion systems is a propulsion system based on antimatter. Antimatter, coming into contact with matter, annihilates both particles, releasing huge amounts of energy. A spaceship powered by antimatter can theoretically reach speeds approaching a significant fraction of the speed of light. The potential of antimatter propulsion is staggering, but so are the challenges. Antimatter production is currently a highly inefficient and expensive process, and its safe storage represents additional challenges due to its highly reactive nature. Despite these obstacles, antimatter research continues as it promises to be an unprecedentedly efficient engine. Huge distances present the most obvious obstacle. Nevertheless, even with a modestly efficient propulsion system, only a fraction of the difficulties would be overcome. Interstellar travel is an enormous undertaking fraught with technical and logistical challenges. Even with the most advanced propulsion systems, traveling to our nearest star system, Alpha Centauri, requires overcoming enormous technical obstacles. One of the main technical problems is protection against radiation. Space is filled with high-energy particles from the Sun and distant space sources. Prolonged exposure to this radiation can be deadly to both humans and sensitive electronic equipment. Modern spacecraft use a combination of physical and electronic shielding to protect against radiation, but these methods are insufficient for the prolonged exposure expected during interstellar travel. Advanced materials and innovative shielding techniques are being explored. These include the use of magnetic fields to deflect charged particles and the development of new composite materials that provide better protection without excessive weight gain. However, creating effective and lightweight radiation shielding remains a major challenge. Another technical hurdle is maintaining the structural integrity of the spacecraft themselves over the long term. Spacecraft designed for interstellar travel must be able to withstand the stresses associated with launch, long stays in space, and possibly collisions with micrometeoroids and other space debris. The high speeds required for interstellar travel exacerbate these risks, since at such speeds even tiny particles can cause significant damage. Engineers are exploring advanced materials such as carbon composites and reinforced alloys to improve spacecraft durability. In addition, modular designs that allow for in-flight repair and maintenance could be critical for long-duration missions. The vast expanse of space presents another logistical challenge. Even at a significant fraction of the speed of light, it would take decades to reach the nearest star systems. Advances in autonomous systems and long-term life support are needed to keep a spacecraft operating reliably for such a long time. Solutions such as hibernation or suspended animation are already being explored, but these technologies are still in the experimental stage. In addition to technical and logistical challenges, interstellar travel faces serious economic and political obstacles. The cost of developing, building, and launching an interstellar mission is astronomical, no pun intended. Governments, private enterprises, and international consortia will have to collaborate and pool resources. Historically, space exploration has been funded primarily by national governments, but the growing involvement of private companies such as SpaceX and Blue Origin suggests a potential shift to more diverse funding models. The search for habitable planets, especially in the Alpha Centauri system, is one of the key areas of modern astronomy. As you may have already realized, the discovery of Proxima Centauri b in 2016 was an important milestone that showed the possibility of habitable worlds in our nearest neighboring star system. This exoplanet has sparked numerous missions and research initiatives aimed at figuring out its characteristics and potential to support life. To continue this research, the European Southern Observatory has developed a new instrument designed specifically to search for exoplanets in the Alpha Centauri system. This advanced instrument, part of the Very Large Telescope in Chile, enhances our ability to detect Earth-like planets by improving the accuracy of radial velocity measurements. The instrument aims to identify Earth-sized planets by detecting the tiny gravitational fluctuations they cause in their host stars. Focusing on Alpha Centauri A and B, the two Sun-like stars in the system, this instrument seeks to detect additional planets that may lie within their habitable zones. The improved sensitivity and resolution of this technology promises to reveal planets that have not previously been detected, giving a clearer picture of the potential for habitable worlds in our nearest star system. The importance of discovering a habitable planet in the Alpha Centauri system cannot be overemphasized. Such a discovery would be a tremendous step forward in our quest to understand how widespread habitable conditions are beyond our solar system. A habitable planet in such close proximity would be a prime candidate for future interstellar missions and a potential target for human colonization. Recent discoveries in the search for habitable exoplanets have been promising. For example, late this spring, astronomers discovered the Earth-like exoplanet Gliese 12b, located just 40 light-years away. This planet, comparable in size to Venus, orbits a red dwarf star and is estimated by scientists to have a surface temperature of about 107 degrees Fahrenheit. The discovery of such a planet, which may have an atmosphere, provides insight into the conditions necessary for a planet to retain an atmosphere and for liquid water to exist. The discovery was made possible by NASA's Transiting Exoplanet Survey satellite, which detects exoplanets by observing a small, dimmer star as the planet passes in front of it. During such transits, the star's light passes through the exoplanet's atmosphere, allowing astronomers to analyze its composition using transmission spectroscopy. The significance of Gliese 12b goes beyond its potential habitability. It serves as a valuable point of comparison for understanding why Earth and Venus, despite their similarities, have very different environments. By studying Gliese 12b, scientists hope to learn more about the atmospheric retention and evolutionary pathways of Earth-like planets orbiting cold stars, which are the most common type of stars in the Milky Way. Gliese 12b's estimated size may be as large as Earth or slightly smaller, comparable to Venus in our solar system. Current efforts to find and study potentially habitable planets around Alpha Centauri and other nearby stars continue to evolve. Instruments such as JWST are expected to play a crucial role in this search, providing a deeper understanding of the conditions that could make these planets habitable. On the other hand, no one is saying that humans should be the first to explore these distant worlds. Even without the advanced technology necessary for human survival, we can still send probes to pave the way. Intelligent robotic probes and artificial intelligence have a key role to play in the future exploration of interstellar space. These technologies can operate autonomously, handling complex tasks without direct human intervention, making them ideal for long-duration missions far beyond our solar system. One of the most intriguing concepts in this regard is the so-called von Neumann probes. These theoretical, self-replicating machines could explore the galaxy using local materials to create their replicas, exponentially increasing the number of probes with each replication. This approach could provide extensive exploration and potential colonization without requiring constant resupply from Earth. However, when it comes down to human space exploration, the idea of interstellar arcs and self-sustaining habitats represents a visionary approach to colonizing distant star systems. These massive spacecraft would host large communities, providing everything needed to sustain life during multi-generational journeys to other stars. These habitats will be equipped with advanced life support systems, agricultural facilities, and social infrastructure to ensure the well-being of their inhabitants. In conclusion, while our current technology limits us to relatively modest space travel, these advanced concepts offer a glimpse into a future in which we can transcend the space barriers that confine us to our solar system. As technology advances, these concepts may well move from science fiction to reality, paving humanity's path to the stars.